I'd like to welcome you all. My name is Alan Lopes. I am the Deputy Superintendent of Critical Events here in ANA, National Agency of Waters. I am followed by different colleagues, and I will introduce them as following according to their speech initially. I'd like to call our director, our president director of our agency, Felipe Sampaio, for his first words. Felipe, if you could say the first word. So good afternoon. Good afternoon, everyone. It's a great pleasure being here and start this workshop for risk management and floods. We know that the frequency and intensity of hydrological events as floods and flash floods has increased year by year due to the effect of climate change and beyond the economic damage. This effect put millions of lives in risk every year in our countries. So the identification of vulnerable areas and floods are an important step to develop adaptation plans, contingency plans, and effective actions to manage the risks to mitigate all the harm caused by the facts we have lived. The lack of a reliable data makes this process something challenging, mainly in countries like ours in a development countries. So our idea to have this workshop, Anna, is gathering different institutions, national, international ones, involved with the risk management of flood to share their experiences. So this workshop aims to gather people with different expertise in this topic, and the common aim to prevent and mitigate all the harm provoked by this event. So our expectation is that this workshop will allow the assessment of opportunities, strategies, improvement, and implementation, sharing of technologies, techniques, and also tools. So these discussions are extremely important to suicide Anna update our atlas of vulnerability, that study that will map the rivers and all vulnerable areas for flooding around our country. So I'd like to make these opening words, thank the organization from ANA team, all the speakers that will participate here and share with us all their experience. And I hope this will be a moment of an exchange of experience to move forward in this so important topic. And each time, each day, we need to know this information. So wish you all an excellent workshop. Alan, the floor is yours. Thank you. Thank you, our director, Philip, for your words. I'd like to then transfer the word for our operation management, Dr. Joaquim Gondin. And I will share right now an introducing presentation. He will talk a little bit about the context of flooding these days in Brazil. I would love Dr. Joaquim, the floor is yours, and I will just show the slide. So thank you. My name is Joaquim Gondin. I am the supervisor of operation and critical events in ANA. And I will try to contextualize a little bit the issue of floods in Brazil. Brazil is a continental country, and as it is, we don't have the same climate, hydrologic condition other countries has, so it's very common in our territory. We face situations of flood in one region and drought in another one. At this time, due to the El Niño, we are facing huge floods in the south of Brazil, and also the biggest drought recorded in the north of Brazil, mainly in the area of Solimões River, Madeira rivers, and Amazon River. Say that initial words, we also have to talk about where Brazilian population is located. Primarily, our locations were done by the coast, so Brazilian population it's more concentrated in that region, in the shore of the country. We also have vast areas in our territory with a low population density. So all these factors lead us to analyze all the flood issue with a wider vision. The sense that this map that is showing with this animation is showing how it happens in our territory month by month, how rains happen. So month by month, we have some areas that are more that we have more sliding flood. So we need to look at that territory with this wider view. On the right side, we have another map that is the map of our average, annual average. And here it shows that we have some regions that have low precipitations, but even these regions can suffer with random phenomena of floods. Next, we can talk about the seasons where we have these floods. We can see that, for instance, we are in our territory from December to March. We have the southeast and center east of Brazil are the regions that have more probability to suffer with floods. And it walks through our territory February to May, northeast. It's more Septentrional. May to August, we have floods in the east side of northeast. In the south region of Brazil, it happens the whole year. So those that works with floods must pay attention in this map to always be prepared to face these times. Next picture, we must see the basic difference. It's very common for us. Scenarios like that, that clears the flooding. It means that it was a time of flooding regarding the message. It's very common for us to have some densities and the water is accumulated and provoke this harm. But for each one of us, we have a sense for measures to correct this. This one, if you look at this, it, there's no speed, just a flood, and the cars are there full of waters and houses. So it shows this weakness in our draining. It's not what we call flooding. Now we see another kind of very common situations in our big cities. We have this water course and we work on them and then we receive the rain and then this water wants to return to the origin. These are very fast events that come from this concentrated and high energy flow. We can only detect it and warn population once the rain happens because there's no possible to make any kind of prediction.
Bom, e nós temos as mais tradicionais, que
We
são
also
esses
have the most traditional ones, the river inundation. It's very common in these rivers, and we have to face situations like that, full of population affected by the situation. So the way to face the situation doesn't happen in the same region. We normally act in the Bank River and another places to correct this kind of situations. And we have a mix in many regions. We have these flash floods and inundations. It means it's a flood with lots of energy that destroy everything on its way. This is what happened in Taquari, Rio Grande do Sul. We have an event like that with a great damage of big flood and destruction of the energy. And what our policies say, we have to work in the prevention and defense against these hydrologic events, critical hydrologic events. So this is one of the main goals of our policies. What is ANA's role in this? It's to promote and plan actions to minimize the effect of drought and inundations. Of course, it's during the national system of hydric events. We work with our national system to prevent this. So ANA acts mainly in actions to prevent and minimize of its effects, the effects of uh, this destruction. This is the role that we have. For that, we have a great hydrometeorological net under our coordination, ANA's coordination, that today have something with 4,029 stations, but these stations aided to understanding that we have with our energy sectors, which we have in ordinance together, joint ordinance that allow us to do it simultaneously. We have more plus around 2,000 stations. So we are the great networking that allow us to make this follow-up of these events and work on the prevention for that. ANA has art of each room to help us in this decision-making process. So we have a room to coordinate when necessary all the events that we are following. But this is done articulated with another agencies and another department. So ANA roles is to supply this hydrologic thing, being the role of another agencies making all the alerts, issue all the alerts that are part of this. So here we have partnerships that we have here together with SEMADEM, Senad, and our national system. And what are the greatest challenges? The greatest one that we have today is to differentiate what is a critical event and what is a hydric crisis. So these events are associated of deviations and variables, have precipitations, soil humidity, while the crises are associated to the lack of infrastructure or preparation mechanisms to answer and manage this. So we have this differentiation around this topic. What we have is to avoid these critical events to become
Bom, e não existe, então,
so there is not only one answer for this crisis in Brazil. So we have a set of solutions that involves necessarily the infrastructure and management strategy. There's not only one answer for this. So this is the initial contextualization that I would like to make, and I wish all of you a great seminar with new technologies and new actions could be presented here. Thank you, Joaquim. So I will transfer now the word quickly. I will transfer the word to our technician for critical events for a brief presentation about floods. I think Elias can share the presentation and then we can move forward. It's a very brief speech, and then so I make this presentation together with Alan. I don't know if you want to say something about the first slides, Alan. The idea here is contextualize a little bit about the size of the problem that we have here. These are information from our National Center of Disaster Alert, and it puts together all the natural disaster that happens in Brazil from 1991 to 2021. So we have here another disaster that are not specifically related to this, but part of these disasters are related to floods and disasters.
Embora o número de desastres seja quarto, o número de afetados que são desabrigados.
We have here the number of people that are affected by these disasters and by flooding, the flash floods, 30%, basically 30% of the disaster people that we have on their numbers from last 30 years that suffered these impacts due to these flash floods, and 40% due to floods. The number of death, most of them is related to this, but also to these flash floods. 30% related to floods. So we have the problem all over Brazil of people that are affected and displaced, and we have to work in our capability to deal with that. And what we are doing is try to update this. The total number of people that are displaced due to this are on our database. And here is presented since 2008.
Reduziu em função de períodos mais secos, vieram na sequência, mas a gente tem patamar aí da ordem de 200.
But we also have something that we try to update every year.
É importante exatamente o objeto do atlas de vulnerabilidade e inundação.
Here we have where these events happen. So Vinicius, I don't know if you want to talk a little bit to us how things are.
Contextualização, vou ser rápido também, só para apresentar para vocês.
Thank you, Alan, for the contextualization, just to present you
por que chegamos nesse
what is the work
Esse é o Atlas,
we
uma
want
visão
to do and why we are here in this webinar. This is an atlas with an overview of vulnerability of floods that Ana did from 2012 to 2014.
Né, para o
And we
país,
already have
de onde seriam os lugares mais afetados por desastres.
our country about where the disasters can happen.
À época, levando em
And
consideração
this atlas was built in that time.
em nível nacional, mas resgatando
taking into account not only the databases that we have in the national level, but
dados,
what we have of
cada estado tinha o seu,
information. And here we have the information about
cada participante da defesa civil
the
tinha
frequency of inundations. Each state used to have its own system, his record,
tem registros, né?
its
Mas
memory
não era banco de dados consolidado. Então você fazia
of
foram as oficinas nos estados e aí tentando
our
resgatar.
actions. We have the registration of this civil defense, but that was not a database, so we tried to rescue different parts of the database that were spread
né, que eram,
around the country. We can put it this way that we had an information system that belonged to each part in each state of the country with their own experience. So we try to characterize the recurrence through the memory of what have happened in the last 10 years. Around 5 to 10 years, gradual flooding events observed over the period of less than 5 years. No flooding last 10 years, and then we categorize in high, medium, or low the frequency of flood, of inundations the same way, the same people, the same database that we had around the country. We tried to differentiate two disasters that were closed, what kind of damage that was observed, if that was affecting critical services, too much problem of lives loss or risk of life of the population, if it has affected severely the essential services, and categorize it to know the size of the damage and put this in a matrix, and this matrix will define the vulnerability of that flood, the frequency compared to the damage. So two parts compound the vulnerabilities, the concept of our atlas that was published in 2014, but the high frequency as a low damage with low vulnerability, high frequency with medium damage, and then we can assemble this matrix in the way it is. It was defined in this way, and we reached this general map we have from Brazil. In the diagram format, but the same explanation in this vulnerability, high, medium, or low. And this is an example that we have. This is the state of Acre. This is an interesting state because the state worked to categorize every part of the river that was important in that state.
Para a atualização desse atlas, o que a gente pretende com a atualização desse atlas?
So here we can understand, here we aims to update this, and I forgot to comment a detail. From the time we saw the database was not together, the federal government structured with a system to protect, and the civil defense have structured a database, and this database then started to show all national information. So today in Brazil, we can say that we have a more consistent database that is general for all states in Brazil about all disasters that are related to natural disasters for natural causes, and also leaking and other kind of problems. But the natural disaster then started to be part of this consolidated database, and this database will be the basis to update this atlas of ANA associated with a database, a hydrologic database that ANA has different stations in our national territory, so we will get the hydrology data to make this database more consistent. That is very good today, but shows some things that we have, some issues that we can fix with the hydrology, not 100%, but we will have more information and use this, the hydrologic registration, to reach the frequency of the disaster. So that would be the main update, and I showed to you a few minutes ago the map of Acre states where we highlighted all rivers. This updated of vulnerability already presented by our president, deputy president, it will focus it in the urban areas. The focus will no longer be the all parts of the rivers, but we should focus on urban area where we can identify the amount of damage, being it human or material. So we use the updated database of our civil defense and hydrology, and to help these two databases that are not perfect. One of the hypotheses that we have in the process, and it has evolved, and Mauricio will present it here in a few minutes, and we could identify the areas with the use of strategies and routines of analysis and use images to reach the quantitative. So we comes from a previous atlas, a more quantitative with the information that were available, and today we will move to an atlas that it's more quantitative, that we use the database and the technology together. So this atlas comes in a very good time to identify the kind of technology we could apply here to check the information that will be part of this vulnerability atlas of vulnerabilities and flood. I thank you for your time, and I wish you an excellent webinar here, because the presentations are from very interesting people. Thank you very much. Thank you, Vinicius. Thank you for this contextualization. This is the kind of problem that we are living today. We needed to update this atlas covering all the sub-notifications, the disasters record, searching for technologies. It's important to hear all people that we talk here today. So thank you, all of you, for being here, for your time. Our apologies for the problems that we have in the beginning in our webinar, but I would like to transfer right now for Dr. Peter Salomon. He is the director. He's the general director of the research center, the Joint Research Center to Manage Disaster Risk for European Commission. So I will give the floor for him, and I'd like to ask him to make his presentation. Thank you.
Thank you. Thanks very much. I hope you can hear me well. Greetings from Italy to Brazil. It's a pleasure to be here today. My name is Peter Salomon, as was already mentioned. I'm working on coordinating the Copernicus Emergency Management Service. I hope so. It's a real pleasure to be here today with you and present management in the Copernicus Emergency Management Service. Today I will now let me go to the next slide. Just a few words, because maybe not everybody is aware about the Copernicus program. The Copernicus program is Europe's Earth observation program, and I'm sure many of you have heard of the Sentinel satellites that are part of this program. But they're not only satellites, we do also have 6 Copernicus services that you see here on the slide that try to take the satellite data together with models, together with observations, and turn them into daily operational products. Now today, the Global Flood Awareness System is part of the Copernicus Emergency Management Service, which is managed by the Joint Research Center where I'm working, and it's operational since 2012. And in a nutshell, what we are doing is with this service is we are trying to provide timely and accurate, in particular, disaster risk management. You can see below here in the slide how we build up the service. It's built around 3 blocks: on-demand mapping, so user activates for any type of disaster and gets very fast satellite-based maps of the disaster, but also can request risk assessments based on the satellite maps. The second block is the early warning and monitoring block, and this is where I'm going to talk about today. We will be looking at the floods component. So there we have systems like the European Flood Awareness System and the Global Flood Awareness System that I'm going to present to you now, which predict floods, forecast floods and their impacts, as well as we have a satellite-based fully automatic global flood monitoring, and you will hear about this in the next presentation of my colleague Wolfgang Wagner. Now let's move on. Just in a nutshell, what is the Global Flood Awareness System? Now, clearly, we are of course a system that provides flood forecasts, but we are aiming to complement the national and regional services and support with this type of information international organizations such as the United Nations, Red Cross, or World Food Programme. So in the case of Brazil, actually, we have a very good working and very long working Semaden and GLOFAS being here really in close exchange. Now, GLOFAS provides global hydrological ensemble forecasts with an output resolution of roughly 5 kilometers on a daily time step, with a forecast horizon of up to 30 days, but also looking at not only at the, actually you'll see later an example on that. We have seasonal an outlook as well, which is of course very relevant in particular for also for low flows. And there's quite a large number of information, additional informations that users can access through the map viewer. So this is, the map viewer is free. You can register and access the latest forecast. But we also produce or provide access to actual the actual raw data. Also use the data itself and not only look at it in a web frame. A very quick look. I'm not going to go into detail how GLOFAS works. Of course, at the core, we have the hydrological model. In this case, we use a model called ListFlood. It's a spatially distributed model that where we put in, of course, a large variety of static input data. So geomorphological land use or land cover data. We use ER5, so reanalysis data to calculate the initial conditions for the forecast. And then for the forecast, we use predictions from the European Center for Medium Range Weather Forecast, ensemble predictions, as well as the seasonal predictions that are then fed into the hydrological model. And then you can see the output, as I said, on the map viewer, as well as accessing data services through, in particular, the climate data store. Now, we do treat GLOFAS a little bit like any weather prediction system. So we regular update the system, and the last major update was done in July this year. Where you see the key elements shown here on the slide, the key new elements. We went from we increased the spatial resolution of the model, going from roughly 10 kilometer to 5 kilometer. You can see on the right-hand side the difference that this makes in particular for the river network. We also updated all the underlying maps that I mentioned before that are necessary for a system like GLOFAS, so really describing the morphology, the land cover, or land use, or soil properties. Then, of course, we had updates also to the actual hydrological model, which is, by the way, an open source model. So anybody can take, go and access the model and download actually also and cut out from the GLOFAS maps the catchment for any catchment in Brazil and start running actually the model him or herself. And last but not least, of course, we also then performed a calibration of the model with all these changes, with almost 2,000 stations. And of course, here we are very grateful because, as you can see in the image on the right-hand side, we also use quite intensely station data coming from ANA. So we have a very good coverage for Brazil in particular. We also use regionalized parameters where we do not have information about a gauging station. Now, in addition to the actual hydrological forecasts, GLOFASS also produces impact forecasts. So, you know, we have heard before, we have to not only look at river flows, but really also the impacts. And in order to do so, we are using a hydraulic model, this flood FP it's called, to provide global scale flood hazard maps at roughly 90-meter resolution, that we, for different return periods, that we are then using and connecting with the hydrological simulations to calculate the impact of the predicted floods. Now, of course, many of our users come back and ask the question, well, how good is actually the system? So we try to be as transparent as possible and share, of course, also the calibration metrics with the users, because we believe it's very important when you want to use a system like GLOFASS that you build up trust into the system. And what you can see here on the map is basically the color blue and purplish, basically showing very good to very good model skill. And of course, we have also areas where the model performs less good, that are shown here in light green and yellow. But overall, as you can see, we have a very good performance of the GLOFASS version 4 for almost all areas around the world. Now, as I said, we are trying to, of course, improve the system always. And so we measure how much better we are with the new version in comparison to the previous one. And this is shown here on the slide. You can see basically on the left, the map where it's dark blue or light blue, we have an improvement in comparison to the previous system. And where it's a little bit light reddish, we have a slight degradation, but overall, practically in all areas, in all regions, we have significantly improved the GLOFASS simulation in this latest version. Again, all this information can be read and found in more detail on our wiki page, which details all this information. Now, let me just, before I come to an end, give you a couple of examples of how GLOFASS is actually used in practice. Now, GLOFASS on the left-hand side, after the workshop, I'm happy to share the slides so you can have a look at all those again. So I was just saying that I wanted to give you, before ending the presentation, a couple of examples of how we use GLOFASS. Now, one of the key, besides having quite a large user base by now, we have more than 12,000 registered and active users. Here on the right-hand side, you see an example of how the Red Cross is using GLOFASS in more than 11 countries all around the world to trigger flood early action protocols together with the National Red Crosses and the National Hydrological and Meteorological Services. They have developed these triggers when a specific GLOFASS forecast exceeds a certain threshold or a certain level. They will start before actually the flood event is happening. They will start to hand out very low cost help, such as water canisters or tents or blankets that are then, once the flood is ongoing, once the emergency is ongoing, are very difficult to get to the people. On this second slide here is also a couple of examples. You can see, for example, that the African Union is, when they have established their multi-hazard early warning and action system for the whole continent of Africa, they're relying in the river flood section also purely on the GLOFASS forecasts. And for those maybe that have seen that the World Meteorological Organization is publishing since a couple of years the state of global water resources. GLOFASS data and output are part of one of the 8 models that are used in these regular global water resources report. And then, as I mentioned, and as I think is also relevant in particular for Brazil this year, is we are also using the GLOFASS forecasts or are used by our colleagues in the drought observatories to produce drought situational reports. And you see here one that was done in April about South America. We are, if I'm not mistaken, the colleagues are in the drought observatory are working on another one again for South America, looking at the drought that is currently ongoing. And this is done also in collaboration with the colleagues from CEMADEN. Now, I'm coming to an end. What are the next steps? We are working already on a couple of minor releases of GLOFASS. I will not go into detail. There will be a couple of improvements based on user feedback. We are but also looking at the next major GLOFASS release, which will again include the number of stations we use for calibration. And this is planned for the second half of 2025. Now, before coming to an end, I would like to invite you. We have annual meetings about GLOFASS and the global flood monitoring that you will hear now from my colleague Wolfgang Wagner. We have not yet published a fixed date, but we'll do so next week. We'll send out a save the date message. So if you want to join, have a look on the GLOFASS webpage. We will publish the news there. It will be an online workshop. And there you will find out much more about GLOFASS and all the other tools that we have in order to do flood risk management. Now, last but not least, please, we are always looking for feedback on GLOFASS to improve the system. Also, if you want to have a reporting point, basically a gauging station in the map viewer for your station that is relevant to you, this is possible. So you can request it by just sending an email to the contact us email address. So I'll stop here. I apologize for this, for the technical problems also from my side. But nevertheless, I hope you found the presentation interesting. And as I said, I'm happy to share the slides afterwards, of course, with everybody. And I'm happy to answer also any kind of questions. Thanks a lot for your attention.
Thank you, Peter. We thank you for the opportunity that you share your presentation, the slides you had with us. Afterwards, it will be very important that is used here in Brazil for different institutions to predict floods in rivers. It's a system that has a global scale, but it has this usage here in Brazil. I would like to ask you to be with us for a few minutes for more time for the discussions, the further discussions we will have. I would like now to call our next speaker. That is Wolfgang Wagner from Technical University of Vienna, and he will talk to us a little bit about the products, the Sentinel products they have for these issues of the identification of areas that are impacted with floods.
So thank you very much for the invitation. It's my very big pleasure to introduce to you the global flood monitoring component. So the slides come from myself and from my team at TLV, and of course the whole Peter Salomon and the whole project team that is developing the service. So including from the Earth Observation Data Center and the German Aerospace Agency, or colleagues from Luxembourg and colleagues from Italy. So as Peter already put the context, our part is only just one of the components of the Copernicus Emergency Management Service. So we are covering just the part on the early warning and monitoring of flooding. There's also an important component which does on-demand mapping, where they use all kind of different satellites data to have the most accurate assessment of flooding using expert analysis of the satellite image. In our case, we use a fully automatic system that is based just on one satellite, the so-called Sentinel-1 satellite of the Copernicus program. The Sentinel-1 satellite is a synthetic aperture radar that is able to see through the clouds and even through rain. So we have the big advantage that while we can see floods even while the flood is ongoing, which is often not the case if you work with optical satellite data. So here you see the Sentinel-1 satellites. Here are the solar panels. This is the antenna from the radar system. And the satellite is sending down pulses to the Earth's surface where the radiation is being reflected, and we record what is coming back, which is then creating the so-called backscatter images. So that's an animation here. It might be fast. You may not probably see it, but it illustrates how we have in regular scenarios 2 satellites from Sentinel-1 that cover the whole Earth's surface. Unfortunately, at the moment, we only have 1 satellite because the second satellite, called Sentinel-1B, suffered an anomaly in December 21. So at the moment, we only are left with Sentinel-1A. We are hoping that the European Space Agency will be able to launch Sentinel-1C roughly in fall next year. And what's a very big strength of the Sentinel-1 satellites is that they have like a monitoring concept. So the satellite has been designed to give maximum global coverage. And it's also programmed to always work in the same measurements mode over land. Unfortunately, for like applications outside Europe, the satellite cannot be switched on all the time. So it can only operate 30% of each orbit. So one orbit takes about 100 minutes. And from those 100 minutes, the sensor can be switched on 30%. So the ESA has to make difficult choices of where to make acquisition. Of course, as it's a European system, the coverage is much better in Europe. And it's also better in some places where you have tectonic active areas. In those areas that you see here in green, unfortunately, these are less well covered. So if you look at Brazil here, say the more 1,000 areas here with agricultural areas, these are better covered. Less well covered is the Amazon forest. There you have acquisitions only every, say, 6 to 12 days, which of course is a long time period if you consider flooding. The way how we can identify flooding in SAR images is by the fact that if we have like a regular land surface, for example, here, this is a rough soil, then a lot of the radiation that is being transmitted by the satellite is being reflected at the surface, and a lot is coming back. If we have a water surface appears smooth for the radar, so it appears like a mirror, and the radiation is scattered in the forward direction. That gives us a very low backscatter signal. So that's why if we have a SAR image that contains water, those water areas appear as black areas here, so very low backscatter. And this is what allows us to classify flood situations. So when we do the automatic analysis of the data, we look for a change from normal backscatter to very low backscatter. So the global flood monitoring service is designed such that it allows global and systematic monitoring. It's also designed such that the images are processed as fast as possible. So we've set up a system that ESA is now also processing the data very quickly after being recorded. Then it's shared on a data hub. We fetch them as fast as possible so that within 6 to 8 hours, the data has been processed and made available as flood maps. This is to support activation requests. Of course, we also built the system such that it allows easy usage so that you have various APIs to use the data on a routine basis. In terms of the spatial resolution, we went for a 20-meter pixel sampling. The extent is global. We have also now an activity to process the complete satellite archive. So that means we do an analysis of all SAR images acquired since 2015, which is possible thanks to the fully automatic algorithms. So what is the advantage of this kind of approach compared to a manual interpretation of SAR images? Well, a big advantage is that you don't lose any time due to human intervention. So no human needs to say, well, please acquire an image. No human needs to take the image and interpret it. So you're very quick in delivering the results. And what we also discovered is obviously many flood events are missed. So when you have this fully automatic analysis, that you discover many unreported events as well. What are disadvantages? A disadvantage is that because you're fully automatically classifying the images, that of course you have false alarms. Essentially, we are looking, say, for the needle in the haystack. So the one flooding in many images where you don't see flooding, And it's of course also a significant processing overhead. But in any case, as we are building a flood archive, I think this overhead is fully justified. So from an operator's point of view, the challenges are the accuracy of the flood maps and the timeliness. Could anybody please confirm that you hear me well and you see the slides well? That would be great.
Everything's fine, Wolfgang. Thank you.
Very good. So this is the overall description of the system. Of course, you also need scientific algorithms for doing this interpretation. And what we are doing in the global flood monitoring is we're using 3 scientific algorithms that have been published in the literature. So one algorithm has been developed by the German Aerospace Agency, DLR. A second algorithm has been developed by our colleagues from the Luxembourg Institute for Science and Technology. And the third algorithm has been developed by my team at the Technical University in Vienna. So we have 3 state-of-the-art algorithms that have different strengths and weaknesses. And we use kind of this opportunity of having 3 different algorithms to better understand the strengths and weaknesses of each of the algorithms. And we create an ensemble. Say if 2 algorithms tell us that it's very likely that we have a flood pixel there, then we identify this pixel as a flooding. And if you have all 3 algorithms agree that there's a flooding, then we can be very certain of. So we have, for example, you see here one case from China, where we have a situation where this dark color shows that all algorithms agree that there's a flooding, and in the lighter color, so you see where 2 or maybe only 1 algorithm identified this is a flood situation. And when we create the ensemble, this is the resulting flood map that you get from the system. Or here's another example from disastrous flooding in Belgium that happened in July of 2021. Here you see in this case, all 3 algorithms agree quite well on the identified flooding scenarios. What these images here also show is of course, that when you have a system, it's not possible to identify flooding everywhere. For example, if you have dense forest, we cannot see through with the radar, so we cannot identify flooding within a dense forest canopy. So, for example, flooding in the Amazon forest, unfortunately, we only see if there's like an open area within the forest. I've also heard that you have a big focus on urban areas. So unfortunately, also in urban areas, the identification of flooding is not that simple because we have complex interaction mechanisms of the microwave radiation with the urban areas. So also those areas need to mask. So the data come not just with the information about where the flooding is, but it also shows us areas where we have no sensitivity, including forests and including urban areas, areas that have backscatter that is overall very low, for example, rivers, permanent rivers, or like airports, topographic distortions, and radar shadows. So the product you can get from Copernicus is the observed flood extent together with historical water mask that shows the expected areas that is like permanent water and seasonal water. Yeah, so and this you can combine. In addition, these are the main layers of the product. In addition to those layers, you get also auxiliary information, like the exclusion masks, where we don't provide the information. We also provide likelihood, so how confident we are in our prediction that this is a flood areas. And we also give advisory flags. So this is like scenarios where it's difficult sometimes to identify flooding. For example, if there's a lot of winds that's roughening a water surface, we try to give a warning that here we might have misclassifications. Or there could also be, like for northern areas, we could have problems with snow and ice that also sometimes may look like a water surface, but it's like wet snow. Additionally, in the products you find and like other auxiliary information. It's like how does it relate to land cover that we're seeing, the population density. You also have metadata on the satellite image itself, and you also get information about the next expected Sentinel-1 image. So in case, for example, if you have an ongoing flood in Brazil and you want to know when is the next image that can come, it's within the service and available. Just to give you one impression about the system, how it's done. So it's built at the Earth Observation Data Center at a cluster of computing machines with over 500 CPUs and 3 terabyte of RAM. And on a typical day, we have a terabyte per day to process. And we do this in a continuous way that while the satellite acquires the data, ESA is receiving the data at some of their stations and making the data available at different hubs. We keep watching when the data become available on the different hubs and get them within 20 minutes. From there, we put it in our processing system within 10 minutes. Then the flood detection is taking place, so that in a very good scenario is, so as soon as a Sentinel-1 image gets available from ESA, we process them within 2 hours and make them available to users. And one of the access points is the GLOFAS map viewer that you can access over this link. It's operated, as I understand, by the ECMWF, European Center for Medium Range Weather Forecasting. We also find all the GLOFAS results that Peter has shown you before. And one of the layers there is also the GFM, where you can, for example, display the images that have been acquired on a certain day. And then you can use the different map backgrounds to identify where flooding is taking place. just to give you an impression of some of the products, I've been lucky, kind of lucky. I was on travel in Bosnia-Herzegovina at the beginning of the year, and at that time was raining quite a lot in Bosnia-Herzegovina, and some of the areas have been flooded. So on my way to the countryside, I saw this quite large stretch of inundated land. And when coming back to the hotel, I checked the web viewer. Then basically I could see the water area identified by Sentinel-1. So these are the two pictures from the locations I've shown before. So this was the road we're driving over. And yeah, then we're keeping over here over this hill, and then from location 3 here, there was also, you could see here a smaller area identifying the Sentinel-1 image. And this is the image from the hill down to this area 3. So even like rather smaller patches of water can be well recognized in the Sentinel-1 data. Of course, if you, for example, look at this one, you mostly see the open water surface. Once you have like this mixture of vegetation and surface water, then it gets difficult for the recognition. So you look mostly at the calm and open water surface in those images. I think our biggest floods that we have observed so far, and the first one where the system really showed its value, was the Pakistan floods that happened from middle of August last year until the end of September. Pakistan is also not that well covered by Sentinel-1, but you see here a typical sequence of images, for example, on the 18th of August, 22th of August, 27th of August, 30th of August. And you see here the progression of flood extend from the first day here to the last day. And obviously, if you have many images, you can combine them and you can start to make maps like flood frequency maps, as also you're planning to create for Brazil, or you have already for many areas for Brazil. So the darker the red here is, the more often we have observed water in this area. So very dark red means for all the images that have been acquired from middle of August to the middle of September, we saw that there was water. And if there's like the brighter colors, it means it was only once or twice covered by water. The total area that was covered by water here in Pakistan was amazing. It was the size of the whole country of Belgium that was underwater during the flooding. What also was made worse in this scenario was that the water stayed for many, many months. So that even, for example, in beginning of December, you saw that huge stretches of land were still covered by water. Or another very drastic example from Europe. In September, there was a major flooding in Greece, where here this area was hit with flooding. Basically, there was a rainfall with almost a year of rainfall within 1 and 2 days. So you see here on the 6th of September, there was only little flooding yet. On the 7th of September, already here, a major area being covered, and in the flood progression, so that if you put all these acquisitions together, so in this case, it was on the 6th of September, 7th of September, 12th September, 13th September, 18th and 19th, then you saw the complete water surface area here. So this was an area covered by over 600 square kilometers. So that means it's like several new lakes have been formed there, and also there the water stayed for quite many weeks, just completely destroying the agricultural production in this area. An event on a much smaller scale is here from Austria. Also Austria was a bit hit by the flooding in July 2021, but on a much smaller area. I'm showing this image because we have worked extensively with this flood case, and we also had very good reference data from high-resolution satellite data from the US company Planet. You see here one Planet image where the flood area can be nicely seen by these brownish colors. This is a flood classification based on Sentinel-2, like a Landsat type of image. And here's our Sentinel-1 classification. So you see it's a bit well, more coarse in a way, the Sentinel-1 classification, but it nicely fits with the optical data. You can also see here a comparison to like an inundation map created by models. So with a return frequency of 30 years, 100 years, 300 years. So overall, there's also a good match of those areas that have been affected. But of course, you also see differences between the projected flood scenario to the real flood scenario. Like when they created this flood scenario, they assumed that the rain would take place over larger areas, so wood coming down from the mountains in the north and mountains from the south. In reality, we only had the water coming down along the river and not to all sides. So that shows the importance that it's important to have model scenarios, but it's also then important to have the real data to check what the affected areas have been. So the global flood monitoring service that we have implemented within the Copernicus emergency management service, and thanks to Peter, it's a first of its kind service on the global scale. And it rests on the success of the way how Sentinel-1 has been designed and it's how it's being operated. We also benefit, of course, from the fact that the data are available on an open manner. And I think Sentinel-1 has also been inspiring some of the follow-on SAR missions that have been also very much implementing this monitoring concept that Sentinel-1 has started. So it's not just the next generation of SAR satellites within the Copernicus program, like here this L-band ROSE-L system, or the next generation of Sentinel-1, but also next year there will be an exciting mission from NASA and the Indians called NISA that will give you flood monitoring capabilities. There's also the RadarSat constellation mission that could be exploited, or the SARCOM mission that also gives very valuable data. Yeah, and maybe the last statement is, despite being just designed for serving emergency response, I think the data you get from GFM can also support the identification of vulnerable areas and help you in the climate adaptation, because you can analyze the complete archive. So, and from this, you can get an understanding of past flood events. And you can also try to learn from very big floodings that happen in other areas and transport this knowledge to hydrologically similar catchments. And with this, I hope I wasn't too long, and I hope I didn't speak too fast for the translation. Thank you very much.
Thank you. Thank you for your presentation. It meets exactly what we are building here about these tools to identify the areas that are impacted by flood. So this is very important. I'd like now to transfer the floor now this time. We are short of time and kind of delayed with presentation, so I will immediately transfer the floor for Mauricio Cordeiro. That is our server here that also work in this area to identify these vulnerable areas using satellite images. So Mauricio, now I give the floor to you. So good afternoon, everyone. My name is Mauricio Cordeiro. I am a public server of ANA. And I work with our superintendent of events in critical situations, and I will show you a little bit of what we are doing in our agency using remote sensing as a supporting tool to update the vulnerability atlas that was presented initially by Vinicius. So the objectives that we have is to update the vulnerability atlas through the quantifiable variables. As Vinicius has mentioned, we started this in 2014 in a qualitative. Now the idea is to change and start to use the quantitative variables now, confirm disaster and events registered by authorities it was also mentioned by Vinicius, we already have a good database today of disasters that can maybe need small adjusts, some things that we know that it is not correct. So looking for disasters that are not registered. And another idea would be estimate the flood-prone urban areas in all municipalities. In this case, it's a very extensive work because we have more than 5,000 municipalities. The initial idea of this work was to use optical images. So here we have a case that happened this year in the city of Montenegro, Rio Grande do Sul. In the south of Brazil, this region was heavily impacted by different events of flood. An initial idea was to use these new images in a technological pack that was developed by me in my doctorship in Toulouse together with my colleagues, Michel and Santiago. But the problem here with these images, I will show you next slide, is that even if you can identify a good covering without clouds in some parts, when we need, for instance, an automized work that cover all the cities and could really quantify it, we can see that the clouds and shadow of clouds will harm this identification work to identify these areas, mainly if we identify that we would use automatized algorithms here. Montenegro, in this case, we mark all the flooding areas, but we did it manually by people from the university in Rio Grande do Sul. But for those that work with this algorithm, know that this presence of clouds and tissues and shadows of clouds would harm the identification of these urban areas. And if we move to another region for the country, for instance, we have another important flood this year in Rio Branco, Acre, close to Amazon River. The flood happened here in April 1st. That was the peak of this flood. If we look to the optical images, of course, we do not get any image to try to mark this, to identify this. So one of the options, very interesting, that this presentation comes after Wolfgang's presentation, is that we tried to find radar images from Sentinel-1 to make this identification. Here is just a visual inspection of this flood of the Rio Branco River that happened in April 1st, 2023. Here the optical image from Google. Here the image before the flood, and this is a SAR image. These images are fixed radiometrically according to the elevation, so it's a higher level to be fixed that these images have. But we can see visually here the possibility to identify some zones of flood. So one of the characteristics of this work differently than what was presented by Peter and Wolfgang, maybe this is the scale thing. Here we will try to focus in urban areas in a very reduced scale. The idea to change to Sentinel-1 is also questioned by some scientific papers. This one is from 2022. It was done in Italy and have assessed the effectiveness of Sentinel-1, that's the radio, and Sentinel-2, that is optical for flood detection, in this case in Europe, and they concluded that on average the 58% of flood events are potentially observed by Sentinel-1 and only 20% by Sentinel-2 due to the cloud coverage. So this is why we had this idea and also to call people from UN that are working with Sentinel-1 to detect this, because we believe this is the best way to make this work. Something that was not mentioned by Wolfgang is in the difficult that we could have here, that is out the areas that are out of Europe. One of the satellites, Sentinel-1, has a malfunctioned problem December 21. In August 22nd, ESA gave up trying to restore this satellite. What provokes that today, the south region of Brazil, it's the region that we are more interested in now. It's the region that does not have imaging coverage by Sentinel. So this is the problem to acquire it. There are another problems in Brazil, but mainly in the south region of Brazil that has this problem of covering. Now moving quickly for what has been effectively done by Ana. The first part is a water detection model. This is a very different model than the one that was presented in the state of art. This is a more simplified model that we are using. We are using a random forest classifier, and that was trained with 26 images of Sentinel-2. These images have a high quality done by CNIS using ALCD masks. These masks are available freely on the internet. They can be downloaded. So what was done in this mashup, the S2 images together with the water mask of the most close images. So this is first component of our simplified model. Another thing that we need in this detection of flood is the baseline, the water baseline, or check the water that is always present in the region, so we could consider it as a flood. In this case, we are using the Global Water Service PECL that was published in Nature magazine in 2016. This data setting has the water occurrence and water recurrence annual one. So here is an example in Rio Grande do Sul state where we have rice crops. We can see that these crops have some occurrence of water and a big recurrence during the whole year in a specific period that is identified as water. So what we are seeing is using this recurrence map as our water baseline, so we can from that time check the water that is not on the baseline be considered as a flood. With that, the first processing that was done, we mapped all disasters that are recorded in this national database, all the disasters that occurred between 2016 and 2020 in the south region of Brazil. From those, we have 700 disasters that are registered as flood or flash floods or inundations. In this case, flash floods. It covers around 430 distinct municipalities that are represented here in this map. But a characteristic, as I have mentioned before, is we work to focus on urban areas. So there is an algorithm that was developed, it was implemented using planetary computer, Microsoft hub, using all the data catalog in this planetary computer, where automatically we focus on the main urban area of that municipality, and from then we keep track from the flood close to the data that was informed, the date that was informed before. This is an example for Rio Grande do Sul state and also Santa Catarina. It was done systematically for 700 disasters registered in South region that we had in this database. So here we already have a result of these disasters. In total, 697 disasters, so we have 697 files in PDF, considering that was detected at least 10 hectares of flooding area. So we consider that they were detected. We could also an average tax of 52% of detection in floods and only 15% of detection in flash floods. This number of 52% matches closely to the paper that I have commented that was published by our colleagues in Italy, that approximately 58% of flood events would be detected by Sentinel-1. So it pleased us with this first version because it shows that we have achieved what was in the research. Here is another example of Uruguaiana. It's another city in Rio Grande do Sul state. What we can see here, we can see all the flood and inundation crossing the river. The problem that we have here is that together with this image that was quickly said by Wolfgang, is that the radar does not penetrate in urban areas. There's an effect where this refraction, where the radar signal reach the water and then reflect back and then receive that reception of the signal in a liquid surface doesn't happen. So to estimate how much of urban area was achieved by this inundation, the analysis is harmed by this radar image. For that, today we are looking for alternatives. This is a matter of research. We are working on it. An initial idea is to use ana.gov.br. Ana.gov.br is a digital model for all South America that corrected the high for forest. These ana.gov.br have been also been used in urban areas, what will happen us a lot. So one issue that we put is that wouldn't be possible to use this DTM to detect the flood-prone area without a hydrodynamic modeling. And why that? Because we need to reproduce this in approximately 5,500 municipalities. So these are some results, and there are some papers that were published. It was published by the LR from Germany, the Aerospatial Center in Germany, where they use another index, geographic index, to help to improve this water mask that was initially identified. Based on this study, what we are doing now is to try to use a hand model, height above nearest drainage, together with the water mask that was obtained by Sentinel-1. This is another example in Alegrete, another city in Rio Grande do Sul state. Here we can clearly see the region that was impacted with the flood. Here we have a global hand, and here we have the identified feeding that we had, and here the extrapolated flood in yellow, and in red the extrapolated flood invading the urban area. So these are still in a research format, looking for some alternative that we could improve this identification of these urban areas that are vulnerable to floods. So there are already some studies using only hand, and we want to present the hand together with the water mask originally comes from Sentinel-1, and now coming to the end, our next steps. One of them is automate the detection workflow for every municipality and the entire time frame of Sentinel-1. It means not only look at that 700 events in that date, but the idea now is to automate it to all municipalities and all the period observed by Sentinel-1. First trial we did, we could see that the identification of some undocumented events seems to be promising. Here is an example of the city Alegrete. Here is the disasters table for Alegrete. So we had events in 2016, 17, and 19, but here is November 2019. And this big part here that we search for news, we see that this biggest flood was not registered or is registered in another date or registered in another municipality, but it's not registered in the correct municipality. So we check that this possibility to use this model that was developed to detect undocumented floods can be something feasible. Still in our next step, something that we think doing here is to improve the model of detection. Instead of using random forest that is pixel based, eventually use a model of deep learning, the CNNs. We theoretically would improve this resolution even while these images have some noises, and CNNs are good for the noise inputs. So this is a proposal of a model that I did. Some of the ideas to be implemented in this model, and you still have to improve some operational issues. The correction of this radiometrically that was fixed, it has problems since 2018, and it needs further investigation and detection together to Microsoft that is responsible for this data set to check what we can do. So in this data set, we can see that this kind of error that we have in the image provoke that we identify more water than from 2018 from now. And in this line, we can clearly see the period of Sentinel-1 that was out of operation in south region of Brazil, as we can see in this graph. Now, as conclusions, what we can see that remote sense can be used to identify this flooding area, since we understand its limitations concerning to urban areas, mailing, spatial resolution, errors of that was very well commented by Professor Wolfgang. An advantage of what have been doing is that today we have a data set absolutely free images corrected remotely. All these RTC, GSF, and ana.gov.br are free. This solution is lightweight, can be run locally in a computer in the cloud. Today it runs in MS Planetary Computer or Google Colab as an instance, and we still need improvements, mainly in the water detection algorithm. We need to talk closely to our colleagues from European Union that use GLOFAS, and also the things how we can extrapolate the water masks that are identified using a land digital model to obtain the percentage of urban area that are really vulnerable. So that's all. Thank you very much, and I thank you all for your attention. Thank you, Mauricio, for your presentation. It shows our efforts to use the satellite images to identify. This time now, I would like to call Dr. Julio Soli from MAP Biomas to make his presentation. thanks him for his presentation. This is a Brazilian institution that is very involved in mapping and the characteristics, the study of characteristics of Brazilian biomes, and have papers on this area that will be very interesting to hear them. Thank you, Alain. I'm just waiting for the sharing command as long as it is available for me. Meanwhile, I thank you, Anna, for this invite on behalf of MAP biomes that already have a cooperation with a National Agency of Water. Thank you once again for Anna for this invite. I suppose that everybody is seeing my screen. I will talk a little bit on behalf of MAP biomes for the urbanized areas in Brazil, because inside in MAP biomes is an initiative that I am one of the coordinators. This is a research net, and we'll talk about this ground occupations is compounded by different institutions. So we are a collaborative net that is looking its aims to the applied science to mitigate climate change. So this is the main goal of MAP biomes as a net. We work with different institutions, teaching institutions as universities, federal or state ones, institutions not linked to universities as ONG, and startups and technology companies linked to the algorithms and mapping. We also have different partnerships, institutional partners and technical partners. We also have the funders to be with us during this work that have been done since 2015 in Brazil. MAP biomes is organized in this way. We are split in biomes, and each one of these biomes are compounded by teams that knows this, so they know exactly the topic. So we have in Amazon, Caatinga, another team in Cerrado, Atlantic Forest for rainforest, Pampa, the Brazilian biomes, and we also has the cross-sectional, the events that happen in all biomes of Brazil, as maneuvering, agriculture, mining, and urban areas that we have. These are what we map in MAP biomes. So our purpose, the main purpose of MAP biomes, is to review the transformation of Brazilian territory through science with precision, agility, and quality, and make knowledge about land cover and land use accessible to seek to the conservation and sustainable management of natural resources as means of combating climate change. So we have different technical cooperations. Here we have different governmental departments from every state, banks, some other technical highlight, but we also have other technical cooperation as ANA. This is one of the agencies that we have a wide cooperation. The main characteristics of MAP biomes, they go through these steps. We always work with time series data for the entire territory from satellite. So our information that are based since 1985, and we produce annual data in collections, as we call here. We are in collection 8 now. These are data from 1985 until 2022, where we process it annually. We work in this processing pixel to pixel. Every pixel that compounds the Brazilian territory land set, that it's around 9.7 billion pixels in Brazil. So we tell this story of this pixel about what have happened when we talk about land cover and use. To do that, we use the algorithms that we have, the classical algorithm in most of case, those that are necessary To do that in a way that we do with too much people, so many people working with us, we work in a decentralized way, using the platform Google Work and our algorithm to use most of the information that we have here. For Beyond to Brazil, Map Biomas already in 14 countries. All South America, you can see that we already have at least a collection of soil cover. Indonesia is the third collection of land cover, but we also have plans to make this mapping in other areas in a global level. It works as following. In Brazil, we use this map. We have a team with a local knowledge that receive a training, and they start to make this mapping, and then we transfer this knowledge for other countries that make their own maps individually. As I said, Ana already is a very important technical partner, has a relation of data entering, where we can provide additional information on our platform, information that are important to collect the information in our biomas. And we make this together for fire forecast. We map areas that intend to have these fires. So we map all the water surfaces in Brazil monthly and annually since 1985. So from this example, one of the data that we can extract from this mapping of water surface in Brazil is this trend that we can observe here. It's the reduction along these 38 years of observed. So if we can make the numbers of this, around 70% of Brazilian territory have lost some water surface. Some waters, we can see the area was very big. This you can see in the red color on the map. But moving forward on this, as a coordinator of urban mapping, we are expanding and extrapolating this relation about the hydric correlation using the data that we produce in map biomas. I will give you some examples how we have advanced in this last collection between 1985 and 2022. So to give you an idea about what it means, quickly about the methodology. The methodology, it's kind of standardized. Each biome has its own algorithms that work in specific ways, but when we talk about urban areas, this is how we create the annual mosaics. So for each year, we collect all information and we get the average of this without shadow of clouds. To compound this in this mosaic, we put together a set of samples. We send this from urban and non-urban places. For urban areas, we are using random forest, and following this classification, we have two other steps. That's the application of the spatial filter, and the temporal filter is to ensure that this framework that we are applying, some morphological as elimination of groups of pixels lower than 20, these are holes that we cannot insert at least 30 pixels in this hole. And then we have a last step to adjust temporarily this series to eliminate the classification errors that would the temporal filters. We use mobile windows to ensure in a comprehensive way all the comprehension about this information, these regions where we have more confusion. All this information are available to be assessed, the how to do, but also the hubs that we have, the records, the historical can be changed, modified. When we get the resulting data of this processing, there are some things that we can mention about the Brazil urbanized areas from 1985 to 2022. We had approximately 1.2 million hectares in 1985, and we reached 2022 with 3.7 million of hectares. So today, urban area in Brazil represents 0.44% of Brazilian territory. Seems to be something small, but Brazil it's a very big country. Just to give you an idea, if you compare with the area occupied by soy in Brazil, it's double than the urban area in Brazil. So Brazil has a very big territory. We can see that there is still a strong concentration in this urban area in Brazil. The first one is Brazil, followed by Brasília, Rio de Janeiro. This is something historical, but this process has been changed, as I mentioned. Basically, the urban area is tripled the size that it used to have in the beginning of the last 4 decades. We can observe something that in 1985 there were only 27 urban concentrations that were bigger than 5,000 hectares. So in 85, 27 of this urban agglomeration. In 2022, we reached 97 concentrations with at least 5,000 hectares. So we can see that these urban concentrations have increased a lot along the time and have expanded to other regions of Brazil, to beyond of our southeastern region. But even more interesting than this is that even with this urban growth, it's being reduced and it's reducing in a slowing path. If we look to the urban area as a whole, but if we split this for this according to the size of big cities, the big city has an average of growth of 2.6%. So if we look to the small cities, municipalities of 100,000 inhabitants, the growth is 3.6% to the year. The small cities growth faster than the big concentration. So we have this horizontal trend bigger than what we have done. So with this information, the first approach that we could do to understand and characterize better this urban growth, we make a cross-sectional approach. The favela slums areas that is measured by IBGE, with another information that we have available as a zone risk, the cross-section that I will show with you. So this is all done by Semadane and IBGE, and we had this result of polygonals with different risks of inundations according to their definition. But looking to this urban expansion that we call favelas, these areas defined with at least 50 houses. To compound this, there is absence of basic services and also land problems. The definitions that is put by IBGE, you can see that every 20 years the areas occupied by favelas in Brazil doubles. So in this growth of 1.2 to 3.6, it means 3 times the growth of our Brazilian population. If you look at the favelas, the same information showed a growth of 4 times. So among all the urban growth, 5% of it happening in some favelas. So we can see that between 1985 and 2022, favelas growth 124,000 hectares. And we could understand better that would be 124 football field, Brazilian soccer. So some cities, for instance, capitals like Manaus and Belém, we can get everything that growth between 1985 and 2022. At least half of these 2 cities were in favelas, in these more precarious areas with some susceptibility. Of course, in another cities, this growth was even bigger. I was just mentioning the capital cities as an example, but this is something very strong that shows this favelization process mainly in the northeast of Brazil. Beyond this, we can observe here that when we compare this growth of urban areas to the polygonal and risky areas generated by SEMADEN, every 100 hectares of urbanized areas that grow in favelas in Brazil, 16.5% of these hectares were in one of the zones mapped. For instance, when you look to the biomas, we can see that this growth process in favela in risky areas, 16.5% of everything that growth. When you look at Cerrado bioma, this growth was the biggest one. It growth basically 6 times. So today, urban area in Brazil as a whole, considering this cross-sectional process, we have around 123,000 hectares in areas of risk. And when we look at just the year of 2022, the last of the series, 3% of urbanized area in Brazil are in risk areas. But when we look only to favelas, 18% of all favela area is in a risk area. These images are can give you a very good example of what had happened in Brazil. In the beginning of this year, January and February, an extreme rain event in São Paulo, especially here where you can see in the planet image, the scars of these slidings happened where we had more than 60 deaths, and it happened, most of them happened in favela. To move forward in the hand model, a very interesting cross-sectional step we did, and we are thinking about doing this, is to get these urban areas and understand how it relates to the proximity of the water course. So using hand model, we have this vertically, each pixel of the hydric body, the closer hydric body, we did this cross-sectional of the whole Brazil with the urban areas of every year. We produce in map biomas, and we subdivided this hand model in some strips. So we have separated this model until a closer relation 6 to 6, 12 to 30, and more than 30 meters to understand how was the dynamic of this urban strips of occupation. So we could see not only these 3 first meters of proximity, 68% of this occupation occurred in the last 38 years. So this is a relatively new movement for last 4 decades. And if we look only to the year of 2022, we have in the situation the urban area with 3 square meters of here, we have 425,000 hectares of the urbanized area up to 3 meters. So to give you a more understandable number, every 100 hectares we have in Brazil last 4 decades, 11.5% were in some susceptible area of inundation. And with that, I'm saying the first 3 meters. I'm not defining the susceptibility of this. But when we look at favelas, while in urbanized area 11 of hectares every 100, in favelas 17 every of 100 where areas are susceptible to floods. So we have that according to the close they are to the river, more susceptible they are here. We can see the models of the Taquari River in the south region of Brazil, great tragedy we had with these models that were mapped by Federal University of Rio Grande do Sul, and I put in this over the hand model to have something more accurate. Basically 80% of all models that were mapped by them are exactly in these 3 first meters of this cross-sectional model of map biomas, this hand model. Of course, we also look at another possible problems that has as a trigger the hydric issue, the slidings, for instance, with strong flows, with frequency intensity will make these problems even bigger. So look at how long they have growth in urban area in Brazil. When I talk about the declination, it's what's defined in the law from 1979. It's the law about urban land cover and land use. And we can observe that for most of the 98.8% of this urbanization is not in this area, are lower than 30%, but what growth in this area grows a lot, it grows 5 times compared to what you can move. And of course, it was already presented here with a high quality, the information of the atlas. Here we are not mentioning about the disaster regarding to flood, flash floods and others, all the disaster, but the correlation of incidence of these disasters compared to 1991 to 2022 to the growth of the urban area. So we can see the incidence, the amount of disasters occurred by urban area has growth. You see the curve of growth. When we see this incidence of this disaster by unity of urbanized has also grown 5 times in the last 40 years. So coming to the end, just to remind you, this part of map biomas are the people that have worked closely. Just to remind you, that's not something that I do alone. Map biomas is a very big institution. So these are the people that have worked in the urbanized area. I will stop right here. And once again, I thank you for the opportunity, and I'm open to discuss these issues. Thank you, Julio. Very interesting this work you are doing. We didn't have a complete knowledge. We have worked with map biomas. We have worked a map for water surface and also the deforestation, but this interaction of water in the urban area, it's extremely interesting. So we need to talk more certainly about this. This is the first event about this topic to update the Atlas of Vulnerability. I will ask Ana Carolina if she's here listening to us. Yes, she is. I just logged in. Hi, Ana Carolina. Welcome. Thank you for being here. Sorry for our delay in our webinar. If you could also present yourself and then you make your presentation.
Sure. So I'm going to switch to English here because I know Jim is on the call and I want to see if he can hear me and if he can also see the slides.
Carolina, I can see and hear you.
Yay, good to see you, Jim. Thank you for joining us. You learned some Portuguese right now, right?
I'm learning a lot. Yeah, thank you.
Good. So I'm going to introduce myself. Do you want to go first, Jim, and introduce yourself?
Thank you, Carolina. My name is Jim Murley. I'm the Chief Resilience Officer for Miami-Dade County. That's the large urban county where the city of Miami is located, and happy to be able to participate with my partner, Carolina.
And yes, I'm Carolina Maran, and I am the Chief Resilience Officer for the Water Management District. So working very closely with Miami in all resiliency water-related questions. Jim and myself work very, very close. We have a lot of projects that we develop in partnership. So I'm happy to be here with him and this panel. So I'm going to start focusing a lot on the Water Management District. I was asked to give an introduction and some of the main points, but then towards the end, I'm going to let Jim talk a little bit about the studies that we are developing right now in partnership with the Army Corps. So without further ado, and I know we are kind of rushing to get some time recover here, I'm going to jump straight to an overview of the presentation. So 3 main topics. I'm going to first talk about observed trends in future water and climate projections. We have been doing some innovative work here, especially on identifying future rainfall. So I'm going to talk a little bit about that. How we detect flood observations in general and how we are kind of mapping flood risks, and then using modeling tools as well. So those are the 3 main topics, and I'm going to include a lot of the studies that we are doing to go over the scenarios. So Water Management District, we have 5 in the state of Florida. We are the largest and the most populated one. The very first one that was created Our mission includes mainly, this is the reason we were created. So first and foremost, flood protection. We need to protect communities from flooding. We also have a huge mission of ensuring water supply for all the population here in South Florida, and also for agricultural needs and the environment. And we lead one of the largest, if not the largest, environmental restoration project in the US, in the world, Everglades restoration project. So we have significant number of projects really focusing on really restoring our ecosystem here in South Florida. Very extensive network, and I'm going to talk a little bit about these numbers in terms of what does it mean to have a massive water management system here in South Florida. So we know that Florida is a flat, very flat, low-lying area. We are basically a swamp, and in order to develop and live here, we needed to drain the land. So we needed to remove water from the land to allow for development to occur. And that happened in the early 1940s. And in 1948, after a series of major flood disasters occur in Florida, this project was authorized by the Congress. And this massive system, it's a drainage system to drain water out and allow for the development, it started to be building. So the system, we call it CNSF, Central and Southern Florida. It's a 70-year-old system today. And we continue to manage, improve, restore, and really to be able to continue to provide all the needs that we have in this region in terms of flood protection, water supply, and the ecosystem needs. So just main elements, and I'm going to glance through this slide. So what the project did back in the 1940s was really to allow these two pink rivers to really be channelized. So the lake used to not have this connection directly to the east and west coast. Now we have two major rivers that really allow this discharge from the lake to the coast. We have a dike around the lake to protect all the communities downstream. It's a major dike. We have also a protected area that we regulate water levels for agricultural. This is the Everglades agricultural area, and you have levees around it. We have water conservation areas, again, protected by levees. You can see the green area there. And then throughout the cream area, especially on the East Coast, is where we really live, where we have population, and we have salinity structures. Basically, we control saltwater intrusion. We allow us to have fresh water for water supply because we are seeking to hold salt water to the ocean side. So that's basically the main components of the system. And in the secondary system, and even at the tertiary, we have a lot of lakes and other conveyance storage that are operated by homeowners associations and private landowners. We monitor this system 24/7, real-time data. We have to operate and maintain levels in a very, very close system, and we have to be able to understand those water levels at every second of the day. We are going through a major rainfall today, actually, right by levels even more closely when we are going through those large storms like we are dealing with one today. This is this is traditionally a dry season. This is a result of El Nino. We are facing this extreme rainfall events happening during the dry season. This is the second one in a row that we have in the last, I would say, less than a month. And we are managing the system to be able to respond to those events. Development. So in the project, I talk about the canals, those pumps. When the system was designed 7 years ago, we assume an area that would be urban, like the yellow, orange, the yellow shaded area in the map. And we can see significant population development. So from 2 million at the time, climate changing conditions. So really, We are looking and monitoring very closely those changed conditions we have here on the right. It's a link you can navigate later, but it's our water and climate resilience metrics. So we monitor trends in rainfall seasonality, wet season, monitor sea level. So we have a very extensive network of tide gauges throughout the coast. We monitor saltwater intrusion, ground evapotranspiration. We are monitoring estuarine migration. So really how these mangrove areas are migrating inland as a result of sea level rise. And finally, as part of the environmental side of the things too, we are losing in terms of soil due to the sea level rise. So when we have soil subsidence, really peat that is lost because of saltwater intrusion. So we are monitoring those conditions very close. We have data there linked to the overall public and all the stakeholders in the region. Here's just the DB hydro system, and this is just the plot showing a very steady, significant trend upwards in sea level rises, in sea level rise here near the coast. In terms of projection, I'm going to jump straight to rainfall projections. This is one of our more recent efforts here in the region. We partner with the USGS, and we really look at every available downscaling data set at this point in the region, and we look at how those climate models are really fully able to represent rainfall in South Florida, and not only just rainfall in general, but like extreme rainfall. A lot of those events in South Florida are driven by convective, by those climate models. So we work very closely to review the science, to understand what we have out there, to refine those evaluations. And the latest and greatest report that we have in partnership with the USGS, return frequency period, we have calculated based on all this large set of climate models and downscaling data, a percent increase of rainfall into the future. So 30 years, 50 years from now, what the models are telling us. And I have links here. Again, it really helps us to really map those flood risks into the future. We have also a portal along with what we have been using at the agency. So again, we have multi-level governments here, and we are hoping that we can use those planning elements in a consistent way. Just to give you an example, this is the numbers that we have for Miami. So what we see here is 1.06. This indicates a 6% increase seeing a larger increase, and also you can see a larger range there. But basically for the 1 in 100-year event, which is one of the most widely used for planning purposes, a lot of those local governments have been using this 20% increase based on the latest and greatest the rainfall frequency, the numbers for this for here in South Florida. One more effort that we have been as part of the metrics as well is really looking at flood. We have limitations in how much flood data we have organized. Information resource. Actually, this week was the launch of this tool here. And we have here basically a map that shows all the past occurrence flood events. And we are using some newest technology to also help us in integrating all this information into this portal now. Combination of many different tools that we use to measure flood risk here. Staff reports, flood sensors. We have environmental condition teams that can go to the field and measure high water mark. Anytime we activate our emergency operations center during major events, we send people to the field to measure high on surveys and a series of other technology. This is what I told about here in South Florida. So we have a series of data sets combined here in this flood resource that was put together this week. And I know the organizers, Alan and Mauricio asked me to focus a little bit on this new technology. It's ICE. I have the link here if you want to check. So this is, we have a series of F data, high water marks, sensors, and all of that, but we're still not able to fully capture flood extension in the region. We have been playing with a series of different data produced at a more high level, like larger areas, and we were not able to find any one that could give us the results that we were expecting until we were exposed to this ICE. This is actually a radar. It's a SAR data, newest technology that can really go through the clouds. A lot of of course, everywhere the flood events occur when we have a ton of clouds on the sky, and that limits the capacity of using other satellite data. But this technology here really goes through the cloud. And we are excited because it's fairly new for us. We are doing some analysis. We were exposed to that last year during Hurricane, and all the results that we got are showing very promising. So we have been working very closely with our GIS team to fully interpret this. Just a quick glance of 2 areas impacted by Ian, and which was this technology, the SAR technology in those areas. We tested, we compare, and our comparison quickly on what this tool is bringing to us. So basically in yellow, what you have there is what we call flood-prone areas. We knew those areas were flooding in the past. We knew there were kind of areas that require some attention, and we should direct resources like teams going out in the satellite images. So we also knew that we had the FEMA flood zone. So also the greenish delineated areas are where we see the highest risks according to the FEMA approach. And we had in purple there, basically what we map using only LiDAR data. So based on elevation, on land elevation, and what we call a beta model, we were able to estimate, like we have water level sensors everywhere. So we were able to estimate flood extension based on those water levels using only land elevation. So what you see in pink is what we were able to map only using land elevation. And here comes the blue, the dark blue, marine blue, ICE results, which were really results that none of our tools capture. So areas that were flooded that we were not able to capture or were not documented by any other source. And even this bathtub land analysis was not able to capture, because this is, again, flood driven by other different aspects. So everything in blue here are areas that we validated flood after the hurricane event, and that, again, were captured through this ICE SAR technology. So we are learning, we have the satellites redirected to South Florida right now to monitor this rainfall event that is coming, and we're going to continue to be testing those tools. So data, I focus a lot on data, and now let's move to modeling, because yes, all this data is used for us to be able to do those scenarios, to look at what are the risks. We have a program in place in our agency, the Flood Protection Level of Service Program. It's a program that is out there for about a decade now, 10 years. We assess basin by basin, where we have, of course, population and business and areas that we need to protect. So you see here in red, all the most vulnerable areas, and also in dash lines where we completed the study. So we have about, I would say a little bit over half of our territory where the program is focused, already mapped. We use very advanced tools. We use future scenarios, so future land use changes, sea level rise. We look at +1, +2, and +3 feet, and extreme rainfall, as I said, an average of about 20% increase for the 50-year scenario. So this program really helps us to have the picture, the vulnerability picture of our region, and what kind of measures we need to do to increase this system capacity. So we have metrics, very specific metrics. We look at canal levels, discharge capacity, flood depths on dry land, how long duration of the flood, and also the tidal structure itself, that salinity barrier that I mentioned earlier. So what is the capacity of that structure to discharge? Recognizing that we have higher sea levels in our structures, the system as a whole is a gravity system. So to discharge through higher levels, we have already reduced significantly our capacity, because again, just the gravity is not helping us. The higher sea levels is not helping us to have an efficient discharge. So we have already lost significant capacity based on comparing to what was designed for those structures. We use very advanced modeling tools. We have advanced agent age tools. In most of the basins, we have been using Mike DHI, Mike Shee, Mike Hydro River. This tool allows us to look at overland flow to the unsaturated flow. We have really high interaction with groundwater here in South Florida. You can see the limestone on the bottom left. So we have a very, very, very intense interaction between groundwater and surface water, and we need to fully model this interaction when we are looking at flood risks. So we look at groundwater, unsaturated flow, the overland flow, and all the hydrodynamic elements there. Sorry, hydrologic and hydraulic elements there that we need to account for when looking at inland flooding risks. Something that we are doing more recently is to integrate that inland tools, flood risk tools, to the hydrodynamic. So how do the coastal is impacting flood risks, and looking at compound flooding impacts. So really looking at surge and how surge combined with rainfall and drainage as a whole and groundwater levels is really exacerbating flood conditions here in South Florida. We run in those models also the solutions. So we look at what can we do in the system to increase flood protection. So we look at several different types of projects, including seawalls, pumps. We have a lot of pumps being proposed right now, emergency detention basins, flood walls in general, flap gates, really allowing the water to just go in one direction. This is something that we are needing more and more, and really any kind of flood barrier that we can think of. Something also that we have been looking very closely is on a more basin-wide strategy, like storage needs that we need, and maximizing how much of the green infrastructure, how much of the more natural areas, the more floodplain areas can help us in reducing those risks. So going back again to a lot of those ecosystem restoration strategies, floodplain management in a more natural way, and using nature in our favor. So we have a lot of projects also looking at that here in the region. And we work very closely with the Corps. I'm transitioning now to Jim's part of this presentation quickly, but it's important to understand that, as I said, like coastal, surge risks, inland draining, levees, canals, storage, green natural areas, acquiring properties, moving properties away, determining flood evacuation areas, really adding any kind of breakwater and protecting the shore as a whole with living shorelines. Those are all the types of solutions that we are looking at as part of flood risk management strategies, and they need to be looked at in an integrated way. It's not just one agency, it's a series of agencies, it's federal, state, and local governments working together, so we can think about those strategy and combine a plan here on how we can implement that. Right now, as the South Florida Water Management District, we have two major studies that were authorized for us to develop with the Corps. So in the flood risk management area, I'm not talking about ecosystem restoration. We have the huge SERP project, but flood risk management, we have the CNSF, so our management system, CNSF Section 216 study. It's a flood resiliency study, really a one purpose, mainly flood resiliency risks there, and really looking at how we can increase really protection of high-risk urban watersheds in Southeast Florida. So the most vulnerable area highlighted in yellow here is really the focus of this 216 study that we have right now developing with the Corps. We are on the round one, developing alternatives, so looking at the solutions that can help us attenuate flood risks there. So using a lot of what we learned as an agency already and working very closely with the Corps. And next, as soon as we complete this study, we're beginning already to look at the comprehensive CNSF study. So the whole CNSF system, what else do we need to do? What are the other areas that are vulnerable? So this is going to be a much larger type of study with a lot of purposes. So not only focusing on flood risks, but definitely integrating further the coastal risks and additional elements that we have, all the purposes of this this project here. With that, I'm going to really transition to Jim. Here is just I'm entering to what Miami-Dade is also partnering with the Corps in a more local scale. So they are the local sponsor for all the coastal risk management studies being developed right now in South Florida. And Jim, I'm going to let you talk about the back day now.
Thank you, Carolina. Can I do a sound check? Am I coming through okay?
Yes, you can. If you wanna share, I will stop here.
No, I just want to be sure my sound was coming through.
Yes, I can hear you. Yes.
Can you hear me?
Perfect.
All right. Thank you. And thank you to all our to the hosts and the many people who have joined us. I would say from the outset, I represent one of the 17 large counties that Carolina's regional agency provides science information, data, and operations of the canal system. So as a local government, we are very dependent on working closely with our regional water management district. And I think you saw from her presentation the great depth of detail that they can go into. A lot, suffice it to say, the graphic images that you see trade down on the slide just basically would not be possible without the regional water drainage and water supply system. And that therefore it's a constant every day, every hour of the day, every year managed system in order to maintain. And the challenge was, as we understood that, we realized that with sea level rise, we couldn't rely on the extrapolating the past data, our experiences from the past. We had to understand the science was telling us that the systems that Carolina described to you had to be upgraded, or we wouldn't be able to have that beautiful landscape, which is a mixture of an urban and natural landscape. And that's my task as a chief resilience officer, is to take the data and the information that we get from our regional scientists to take advantage of the capabilities of at the national level. The United States government has the United States Corps of Engineers. They do work all over our country. In fact, and many times they work overseas. And they're a very valuable partner. So the far right of this graphic, you'll see the Key Biscayne Coastal Risk Management Study, CSRM. That's where I am today. I'm literally sitting in the village of Key Biscayne's office. The Corps of Engineers in the village is in the next room. I came out in order to participate. Carolina made sure I was on time. And this, I think, reflects the fact that the solutions that we're looking at across that graphic landscape are different. Out on the Berry Island, we're facing on one side the Atlantic Ocean in an area that often is subject to storm surge from hurricanes or just large storm systems that create erosion effects on our beaches, which are like in Brazil. You know, the beaches of South Florida are one of the most important tourism and natural resources we have. So we have to manage the beaches. We have to manage the coral reefs offshore, which are actually nature's way of breaking down some of the energy of the storm surge from hurricanes. But now we inhabit that Berry Island with a lot of people, and we have to make sure that we are thinking about removing them from the danger of a hurricane. But it's more than that. Even at high tides, with large storm events, we have flooding that Carolina described. That at king tides in the fall, sometimes the systems are flooding salt water during a sunny day. And so our population understands now that the future is not going to look like the past, and we have to engage and invest funds in making changes in the landscape to protect ourselves from catastrophic storms, but to actually deal with day-to-day flooding differently than we have in the past. So the challenge for a local government is to balance these different studies. We have going on at any one time a study that looks at the islands that are important to our entire landscape, that what we call the Back Bay, or it's basically its size differs depending on how if there's a estuary or just a large canal system running between the Barrier Islands and the mainland. And often there'll be a major navigation feature. The Port of Miami is the largest cruise ship port in the world, so we have to maintain the access channel and also protect that economic resource because of its importance to our community. And then as we move inland, we have 3 million people that we have living from the downtown Miami with its famous high-rise towers all the way out to the edge of the Everglades, where we have farming and other much more rural activities. So it's a constant balance working with our partners to take the data, make the day-to-day decisions, but also make the long-term investments. That's the same thing that, in a way we've seen portrayed in the COP28 discussions. How do you understand how to deal with a carbon-based economy that's heating the atmosphere, which expands the oceans, brings extreme heat to the people who are living on the land, and oxidation of the oceans themselves. So we are a part of that process that takes place all over the world, in Brazil and here in the state of Florida and in South Florida. Understanding how the legacy of how we got to where we are today. Mistakes were made, but that's why a large part of what we do with our partners from the federal government and the regional government is restoration. Really, we're trying to fix those mistakes. At the same time, balance the needs that the system provides to people, agriculture, and the environment. And then as we go forward, it's important to have the kinds of discussions we're having right now. We have the fact that we can use technology to have these meetings without traveling. It does reduce carbon emissions, and that's good. But we also, I think, benefit from having the face-to-face meetings when it's possible. And we work very closely with our universities, University of Miami, Florida International University, University of Florida. They're all present and have research facilities that both Carolina's department and we use to help us stay up to date and to train the important new employees that are going to be working in our institutions. So we welcome this the opportunity. I certainly wasn't sure when Carolina said, "Would you like to participate in this?" if I was the right fit, but just listening where I could and understanding that we share a lot of issues, and that we have a large Argentine community here in Miami. So please, if you ever visit and you're interested, let us know you're coming, and we're glad to do briefings at our office. Carolina has a branch office down here with her staff, so we would welcome the opportunity to provide on-site visits and talk through the problems and solutions that we're all dealing with. Thanks, Carolina.
Thank you, Jim. So, Alan, Mauricio, I think we're back to you. Our last slide here is just if you want to get involved, we have links here for you to subscribe to our newsletter and opening for questions.
Thank you, Ana Carolina. Thank you, Jim, for your words, for your explanations. And I'd like to ask if someone has any question, comment. I have asked people to write it down on chat. And I would like to ask you if you could be with us for more minutes. Maybe one of these questions you could answer then directly. Okay, no issues. And now can we share the presentation, your presentation with the public? I will send it back. I will make it on PDF if necessary. And then you can share and you continue to coordinate. And once again, if someone need any kind of information, be in contact. I will type my email here on the chat, and you have all the links of this presentation, all the things you have said here, so you can access here and just send questions today, tomorrow, whenever you need it. Thank you very much. I really appreciate it.
Hey, Alan, are you hearing me okay?
Yes, I'm hearing you, Bill. How are you?
Okay, great. Hey, I'm good. I had to call into the meeting, so are you able to get the translation if I use the phone to call in?
Yes, the translation is going on, so we can speak in English, and we have the translators translating everything you're saying into Portuguese.
Okay.
Can you share your
perfecto.
screen?
Hey, it says it's disabled, but if you would just enable that, I can share.
Yeah.
Okay, great. Well, boa tarde a todos. It's great to see so many good old friends on the line here today, and to be working again with the National Water Agency, ANA. We have a long partnership between the U.S. Army Corps of Engineers and our partners in Brazil. So it's my pleasure to give you a short presentation today about the U.S. Army Corps of Engineers and what our newer developments are when it comes to climate change in the area of flood risk management. For those who maybe are not so familiar with the U.S. Army Corps of Engineers, we are the nation's engineering and construction company. We are a service provider of engineering and construction services to partner agencies like the Department of Defense, the Department of Veterans Affairs, and other partners across the federal government in the United States. And then we also have congressionally authorized authorities to pursue various different types of projects, including flood risk management projects. We have other authorities as well, like ecosystem restoration, navigation, water supply, and hydropower. And so all of these business lines or mission areas are in some way or another all related to water. And because of that connection to the hydrologic cycle, that means they are all exposed to the effects of climate change. So we have a policy and we have a plan when it comes to climate change. And I'm showing you here on the screen a little bit of an excerpt from our policy statement that was signed by our political leader, the Assistant Secretary of the Army for Civil Works. And first of all, it establishes a community of practice that is 300 or 350 or so people across the Army Corps of Engineers who are interested in climate preparedness and resilience and getting ready for the effects of climate change. Of that number, I would describe perhaps 25 as being subject matter experts. And those people are the ones who teach courses, they help us develop new tools, new guidance, new methods, and they help make sure that everybody in the Corps of Engineers knows what they need to know so that they can incorporate climate change considerations into whatever it is that they're doing. I'll also point out that there are other kinds of climate action going on across the Corps of Engineers. We are also working very hard to reduce our emissions, to pursue research and development, to do policy research of various kinds. So climate preparedness and resilience is really all about getting ready for climate change. But there are other types of efforts that need to be pursued as we also get ready. So one quick excerpt from the policy just says, it is our policy to integrate climate change planning and actions into all of our activities. So anything that we're doing, we're going to integrate climate preparedness. And we do this for the purpose of enhancing community resilience with our projects. So this is important. We're not just preparing our projects so that we can have projects that are ready for climate change. The project is there to help the community get ready for climate change. So we just heard from Ana Carolina in Miami, for example. We're pursuing a number of projects right now in South Florida. And if we make those projects prepared for climate change, then South Florida, by extension, will also be better prepared for climate change. So the infrastructure is really just a means to an end. And the real end is helping the community. And we do this using the best available and actionable climate science and climate change information. And the word actionable here is key, because we're not just going to use the latest research. Every time a new paper is published in a journal, we're not going to change our practices. We really have to let the science become mature and actionable so that we can stand on that science and be sure that we aren't going to have to retract and undo something once we've implemented an infrastructure project. So our strategy involves a number of activities. I've listed them here in the lower left. First of all, translating science. We do not expect our engineers to go out and keep up with all of the latest science. So we do that work for them. We synthesize the science, we read the papers, we put together summaries to help people keep up with the science. We embrace uncertainty. We don't run from the fact that climate change is uncertain. We accept that fact and we build it into our decision-making process. We create tools and methods that support repeatable, working level analytical results. And we really want to make sure that our efforts are scaled to the level that is appropriate for the project. So we don't do analysis just to do analysis. We only do enough analysis to support the decision. So sometimes that can be a very broad, simple analysis, and sometimes it has to get very detailed. But it all depends on what decision we're trying to make. And that's also the point of the fourth bullet there is a tiered approach. Start broad, start simple, and only add detail as necessary, as appropriate, considering the decision at hand and the consequences of making an error in that decision. So that's all well and good. We have a policy that supports adaptation and resilience, but let's talk briefly about what it is we actually mean when we say adaptation and resilience. I've put here on the screen the definitions that we use, which come from an executive order from the President, Executive Order 13653. And the key takeaway here is that adaptation is an action. It is a verb. It is something that a person or a system can do. And in particular, the action is adjusting your natural or human system in anticipation of or in response to a changing environment to use opportunities and reduce negative effects. And the example on the right, the figure on the right, is an example of an adaptation approach. So this comes from a researcher, Marjolein Haasnoot, who works at Deltaris in the Netherlands. And it shows here, as sea level is rising over time, there are different strategies that make sense for the coastal flood defenses of the Netherlands. So the initial strategy is shown with the yellow line. And then when the yellow line runs into the sea level curve, the red curve, that approach, that strategy is no longer effective. And so we have a choice. We have to get on the orange line or we have to get on the red line. So it's a bit like taking the metro in Rio, for example. We have to leave the yellow, but we don't know if we want to go to the orange or the red. And so we have choices that can inform adaptation pathways. So by setting up our systems to be adaptable over time, we allow ourselves the ability to monitor conditions, and then when the time comes, make a choice to take a different approach. Now you see at the bottom of the plot, it shows lead times for the action. So the lead time is important because we need to monitor the conditions, and then we need to make a choice with enough time that we are not in an unacceptable condition by the time we make that choice. And then the second definition here is resilience. And resilience is a word that means different things to different people, so it's important to have a clear definition. And again, from the executive order, the definition we use is an ability to anticipate, prepare for, and adapt to changing conditions, and withstand, respond to, and recover from disruption. So whereas adaptation is an action, a thing that someone does, resilience is a trait or an attribute. It is a feature of a person or a community or a system or a project that allows it to prepare, absorb, recover, and adapt. And that's what's shown in the lower left plot. We have a resilience initiative roadmap that explains this prepare, absorb, recover, adapt framework, so that the more resilient our projects are, the better prepared they are for a flood or another disruption, the less damage they suffer when they absorb that disruption, the faster they recover from the damage. And then if you do it right, you can use the opportunity that the disruption offers as a beneficial chance to actually adapt the project to future conditions. So here are a couple of examples. On the left, we have an example from the city of New York. This is in the borough of Queens, New York City, and it is a coastal flood risk management project. It is a combination of a structural project with a nature-based project. So we have a cobble rock berm, a composite seawall that is put inside of a sandy dune. So we have a beach essentially on top of this composite seawall, giving us a hybrid structural and nature-based approach. And on the lower left, you see the triggers, the thresholds, and the lead times that I was referring to when I talked about adaptation pathways. So there's a first trigger there that shows when the sea level rises to the first horizontal blue line, the project is adapted by adding more rock onto the rock feature, adding more sand onto the dune, modifying the stairs and the ramps that people use to access the beach, and thereby getting the performance of that project back to where it was before the sea level rose. And then you see there's a second adaptation threshold with a further adaptation step that involves adding more material onto the dune when the sea level rises to the second trigger level. On the right side of the slide, you can see an example of resilience. So this is an armoring of a levee in New Orleans, Louisiana. So we have a flood risk management project here. The levee keeps the water out of the populated area, but by adding this armoring, which is in the form of an articulated concrete mattress and turf reinforcing plastic mat that the grass grows on top of, we increase the resistance of the levee to erosion. So if the water gets high enough, it may still overtop this levee. We can never build the levee so high that it would never overtop, because Mother Nature can always come up with a bigger flood. But what we can do is we can make the levee strong so that if it does overtop, at least it doesn't wash away and fail catastrophically. So this allows the levee to absorb that disruption and recover faster after the disruption. So Anna talked a little bit about this in the context of Miami. So I'll just show that this is also a picture of Miami. And I'm using this as an example of sea level rise, which is in many ways the first and the largest, most impactful effect of climate change on U.S. Army Corps of Engineers projects. You see here, this woman is waiting for a bus in Miami. There is no hurricane happening. The sky is blue. There's no storm or anything. It's just a high tide and maybe a unfavorable wind. and she's standing in the water because of the sea level rise. So this is something that is already happening now. It is already impacting our communities, and it's already impacting our Corps of Engineers project. Now, the good news about sea level is that it's a fairly simple kind of climate change. The effect of a warming planet on the ocean is fairly well understood. The water expands when it gets warmer, and the world's glaciers and other land-based ice sheets melt and add more volume to the ocean, with the result of that being that if you give it long enough, the sea level is just going to go up. So there is no question that sea level rise will happen, and there's no question of what direction the sea level is going to go. It's just going to go up over time. So whether you're going to plan for a ½ meter of sea level or 1 meter of sea level is really just a question of the speed of change that you're interested in. So there's no uncertainty in the fact that sea level will rise. The only uncertainty is in the rate of change. And so I'm showing here for New York City at the Battery, which is a gauge at the very southern tip of the island of Manhattan. There's a tide gauge there, and we have the observed water levels in blue, and then we have multiple scenarios of future sea level there in the green and the purple and the red. And so those three scenarios are our way of addressing the uncertainty in the rate of change. But remember, there's no uncertainty in the fact of the change. So you could also just think about this as being one curve with 3 speeds instead of 3 curves. So we use multiple future scenarios to address the uncertainty in future sea level. But if you look at that uncertainty at a certain date in the future, if you were building a seawall, for example, in this area, and you said, I don't know what the sea level is going to be in the year 2080. It could be 3 feet higher, it could be 5 feet higher. It turns out that that kind of a question is very difficult for a designer to inform their decisions, because they have an analysis that doesn't really lead them to a clear choice. What we do instead is we take this question and we rotate it 90 degrees. So instead of looking at the uncertainty in sea level in the vertical sense, we look at it in the horizontal or timing sense. So we say, let's imagine that 2 feet of sea level in this case would be a problem for this project. Now we can use the scenarios to put a bracket on that time and say we might see that 2 feet in the year 2050. We might not see that until the year 2100. But either way, we can set up those adaptation pathways so that when the trigger is met, we can adapt the project. So sea level is fairly simple, but we still can make it easier on our engineers with tools. So instead of just giving them a manual or a requirement in a document that says you must do the 3 curves, we have had a lot of success with these online web-based tools. They make analyses faster and cheaper, more consistent across the agency, and also easier on our technical reviewers. So if you have a reviewer who is checking the work of an engineer, they can use the same tool that the engineer used, and they can confirm if they get the same answer. And so we have a better, more consistent product that's easier to check, so we can catch mistakes more easily. And the tool that we have in this case is called the Sea Level Analysis Tool, or SLAT. You are welcome to play with it. The URL there is in the lower left. It is available to the public. So the SLAT will offer the user observed data of water levels and projections of future sea level at over 140 tide gauges around the United States, and also over 1,400 grid points, gridded locations around the United States. And so the user just has to go to their project area, select a gauge of interest or a location of interest, and they can see the observed data, they can see the sea level projections. They can also see extreme water levels. For example, the flood that has a 1% chance of being exceeded per year or a 10% chance of being exceeded per year. Those can also be projected. And we also allow you to look at other agencies' projections of sea level. So we have our scenarios that we use in our guidance, but for example, the state of New York or the state of California, they may have different curves that they use for their guidance. So you can also look at those curves at the same time in the same tool. Now, I said sea level is a simpler kind of a climate change. When we look at hydrology or stream flow in rivers, it is far more complicated. And that's because we just don't have that global scientific consensus like we do with sea level, where the glaciologists and the oceanographers of the world are all pretty much in agreement that future sea level will be somewhere between about 0.3 and 2 meters higher in 2100 than it is now. That's not at all the case when it comes to hydrology and stream flow. Some rivers will go up, some rivers will go down, some rivers will go up and down and become more variable. And also, without that consensus, you get very different answers depending on your choice of model and parameterization of that model and so forth. So what we're showing here on the slide is the modeling chain for looking at future hydrology based on projections of future climate. And you see it starts in the upper left with emission scenarios. We don't know how much carbon human beings are going to put in the atmosphere in the future. So we could end up on a low carbon future or a high carbon future. We just don't know. Then you put that into your global climate models in the lower left. There are many, many different kinds of global climate models, and you're going to get different answers from them. So you have to make some choices there. Then you go to the center bottom. We have downscaling methods. These models are far too coarse in their resolution to be used directly. So we have to make some choices about how to downscale. And Ana Catalina was talking about that, how they did it with the rainfall in Miami. So depending on your choice of downscaling method, you will again get different answers. Then you take the temperature and the precipitation that you have downscaled, you put into a hydrologic model. You have to parameterize that model. There's going to be bias. You must correct that bias out. At every step in the process, you're adding more and more uncertainty and more subjectivity to the point that it just adds up like a tree. And the tree gets wider and wider and wider until you finally get to what we see at the top of the slide, which is a very broad uncertainty in future conditions that makes it very difficult to use those projections directly for engineering design. So instead of using them directly for engineering design, like we do for sea level, we do a different kind of an analysis. We do a bottom-up stress testing kind of an analysis where we start from the potential vulnerabilities to the project instead of starting with the projected conditions facing the project. So this is a different tool, our climate hydrology assessment tool or chat tool. Again, you're welcome to access this yourself. It is publicly available at the URL at the bottom of the screen. And what we've done here is we've taken 32 general circulation models or global climate models, and we have downscaled them, and we have applied 2 different emission scenarios. So we have RCP 4.5 and RCP 8.5. So kind of a lower emissions and a higher emissions future climate scenario. And you can see, and then we've taken the temperature, the precipitation, we put it through a hydrologic model to get runoff, and then we've run the runoff through a routing scheme to get stream flow. So if you look at the upper part of the plot there, this is in the same location as that tide gauge in New York. We have the Hudson River flow change compared to the current conditions or to the simulated past conditions for the low emissions and the high emission scenarios in kind of the middle of the 21st century and then late in the 21st century. And you can see that there are differences from today, but they're very large in uncertainty. And so it's low confidence in sort of exactly what the conditions will be in the future. And you can see the same thing in the bottom plot as well. we have the range of outputs that you get from the different models. Even if you look at the separate emission scenarios, you still have quite a big range in the models. And it can be difficult to use that in a direct engineering design kind of way. So what we do is teams look at the potential vulnerability of the project first, and then what evidence there might be for the kinds of changes that would expose that vulnerability. And this is how it looks in our guidance document. This is our Engineering and Construction Bulletin 2018-14, which is our guidance for how to do this kind of bottom-up stress test analysis. And in this table, what the team does is they look at a particular element of the project. So in the upper row of the table, we have a levee, and we can consider a potential vulnerability where we might have increased precipitation. And the effect of that trigger would be a hazard where flood volumes are going to be larger and they might be more frequent than in the past. So that would be a problem for the levee. And the reason it's a problem is listed in the harm category, where it says that the floodwaters will remain on the levee longer, putting more stress on the levee, increasing the hydrostatic pore pressure, and putting the levee at greater risk of collapse. And then the team has assigned a qualitative likelihood to that hazard of being relatively likely based on the multiple lines of evidence, like the chat tool projections and observations of potential trends in the past data. So they've put all this together and they've said there's a potential hazard here, it's qualitatively likely. And then the key step is, what are we going to do about that? And so the management action that could be recommended in that case would be something like a wider levee. If you make the levee wider now, that means you can add height later as needed without compromising the stability of the levee. So here's an example of how you can do that bottom-up approach that allows you to make decisions under deep uncertainty when you just don't have the ability to predict the future in the hydrologic regime in the same way that you do in the sea level regime. We do have some upcoming efforts that I'd like to highlight briefly. One of them is in the area of compound floods. I know this is also very important to our partners in South Florida. A compound flood is any flood where you have multiple forcing mechanisms at the same time. So you could have a surge in the river, a hurricane storm surge that's propagating up a river at the same time that there's a river flood coming down. And so the two kinds of forcings combine and make a flood that's much worse than it would be with just the river flow or just the storm surge. So if you look at the upper plot, we have a research here from Ahmed Maftakari, who is at the University of California at Irvine. And what he's showing is that if you just run the storm surge model and you just run the hydrology model, and then you take the maximum of the two, you actually underestimate the risk in this crossover area where both processes are important. So we don't want to underestimate the risk in that critical zone. So what we've done is we've partnered with some researchers at the University of Central Florida, Thomas Wall and Robert Jane, and we're looking at some work that they did here in the lower left plot. And they have come up with a better approach for considering the total probability of two kinds of floods occurring at the same time. That takes into consideration the potential correlation of those two variables. So we're working on improving our guidance and improving our tools, because most of our engineers are not interested in becoming statisticians. So we make a tool of this that will make that kind of analysis easier for them to do, so they can get a better answer, but without requiring them to take a lot of expensive university coursework or something along those lines. We're also doing research into when this kind of analysis is even necessary, because if you go way upriver into the headwaters, there's really no need to consider the storm surge at the coast very much. And likewise, when you're on the beach, right on the coast, the flow in the river probably doesn't make very much difference either. So we need to know, where is this crossover point where we actually need to do the analysis. And then we also want to understand more about the durations of these events and what happens if you get two shoulders of the event at the same time rather than just two peaks at the same time. And then one other new emerging effort we have going is our next round of sea level change guidance. So sea level is computed on a 19-year moving average, because that's how long it takes for the Earth and the Moon and the Sun to complete their orbits and return back to where they were and restart the tidal nodal cycle. So every 19 years, the United States government recomputes the sea level, and they're going to be issuing a new sea level in just the next couple of years. So we are going to have to update our guidance and make sure that our three scenarios, our curves, are starting again in the right year so that they can be aligned with the proper sea level. You can see on the upper left plot the change in sea level over time as the government has updated those computations. This example coming from Boston, Massachusetts. At the same time, the government will be updating its geodetic datum as well. So the frame of reference against which we survey the heights of all of our levees, all of our pumps, all of our sea level, sea walls, all of our water surface elevations, for that matter. All of those things are also going to be changing in the next few years because our National Geodetic Survey is also updating its datum. So here's an example from Louisiana. You can see differences of 30 centimeters or more depending on which datum is being used, which geoid model of the Earth's gravity is being used to establish the plane of reference for the surveys. So when the geodetic datum is updated, the height of the ground and the height of the water will change. When the sea level is updated, the height of the ocean will also change. So we need to update our guidance for that. And we're also looking at some other considerations like how to use nonlinear extrapolations of sea level, how to account for possible changes in storm type and storm frequency. So we have a lot to do as we update our sea level guidance in the next few years. And finally, I'll just make a quick pitch here for our tools. Again, the majority of these tools are publicly available. So I invite you to go to our website, which is called Core Climate. If you just Google Core Climate, you will find the website, and you are warmly invited to try our tools and offer any feedback you have on these tools or syntheses or other products. So upper left, again, is the chat tool. In the center, we have a time series toolbox to help you detect any changes in the past in data that you may have interest in. On the right side, we're looking at some syntheses of climate literature. So I really can't stress enough how successful the tools have been for us. It's really been a great accomplishment. It really helps our engineers to do their work. So that's all that I have time for today, but I'll just summarize by saying that it is the policy of the U.S. Army Corps of Engineers that we consider climate change in all of our missions, operations, programs, and projects, that the first and the most impactful climate change we see in most cases is sea level change. But the good news about sea level change is that it's relatively simple. Over time, it just goes up. So if you were expecting 1 meter of sea level change and you only got half a meter of sea level change, just wait longer, because it's really just a question of when. And so that allows us to bracket the future conditions with multiple scenarios. That is not the case when it comes to hydroclimatology. There is just so much uncertainty when it comes to future stream flow that we can't, at this time, create the multiple scenarios approach. So we do it a different way. We use a bottom-up approach that allows us to make decisions under deep uncertainty, beginning with the potential vulnerabilities, and then moving on to the multiple lines of evidence. So once again, I'll just say thank you for the opportunity to speak today. Muito obrigado. Great to see everybody. And if there's any time, I'll take questions, or I can just take them in the chat.
Good afternoon, everyone. I will talk now about our acting in Brazil in this flood issue. So briefly, we have our units. We work all over the country. We cover all our territory. Our mission is to produce and divulgate geoscientific knowledge with excellence, contributed to the improvement of life quality and sustainable development of Brazil. So beyond our acting, we work together with ANA in our hydrological network. This is the net we operate. We operate this since 1970, and it helped us in the second part, that is the flood warning system. This is also a partnership with ANA, and we are working with 17 hydrographic basins, and then we make the detailed situation of each municipality. We follow the floods here. We can see the biggest flood we have in the north region of Brazil, in Amazon, Porto Velho, and different localities. Here it was already mentioned in another presentation, the capacity to surpass the flood. Here, for instance, we have here for Rio Branco, it was done today. You said today, it's another territory, and we are predicting an increase of the level of this river. So we work with short-term and long-term, and we made a reference here. Rio Branco has another level of flood. How do we do that? We have here the reference levels. So we have severe flood, alert and attention. This flood, this level of flood, is when we have this first house, the same place that is impacted. This is an animation that can show a risky area and a damaged area. So this threshold is what we call inundation area. When the damage of the municipality, we can start to see the first damage. And how do we collect this? We go to the field. We have some stations that we operate. We find the same place that was impacted by the flood, and we mark this. So we make all the follow-up with this gauge to check the reference level, and we check this until the lower level. And then we have this reference for this city, and this will be the reference for that municipality. And then we increase the level. We already have some municipalities that would have another kind of damage. So this is the first issue that we work here. For instance, we have a city in Governador Valadares, state of Minas Gerais, the first house that was impacted. This is the level reference, the flood level reference that we have. And we have this hydraulic modeling, where we have different strains that could impact in the city, and we can increase the frequency and the intensity of this flood in each municipality. These are jobs that are done slower because we need to analyze it case by case. We need images with a high quality, optimum quality. We need to collect different data to make this prediction, but we are expanding, so all our alert system are expanding. So these are the two references of levels that we have, that we used to say that we are using, and what is the intention of the flood. We can calculate, and we have all the rain gauges, the pictures of the pluviometric stations that we are collecting to have these references. Another job that we do in the hydrological part here in Brazil, it's the susceptibility map. And then we have the remote sensoring. We have the susceptibility map of 654 municipalities in Brazil, and I show how it is done. We have the city of Uruguaiana Here is the city where we have the houses, and all of this is the Uruguaiana city, and we can see these areas that are the susceptible areas to be affected by a flood. How do we done it in geology? We have different points, a classification that we do, and we have the relief classification, altitude, and we integrate the hand classification and final map. We integrate this. The first part of this classification of these geomorphological characteristics, we understand the geomorphological characteristics of the regions. We have the optical images, and then we can have the limit of each areas that we have. We can say geomorphologically what is the trend of each region, and then we generate a map. Here, for instance, we have a map that is generated for different types of ground and how the areas are classified and they are likely to be impacted by this flood. But then we already have the map. Then we have the altitude problem. So an area that, for instance, has 600 meters, another one that is 5 meters above, they would be susceptible in different ways, one with lower and another with higher susceptibility. And to use that, we use the hand model, fuzzy hand modeling, to detect in those areas that were classified geomorphologically the different things we have a characteristic to identify in medium or low or high risk. And then we have the final map, the models of a high susceptibility, low or medium susceptibility into this, not only the area of that municipality, but the whole municipality. So to finish this, we have in this scenario, we have these two first products, and into what we say the geomorphological thing, we have another product that are the risky areas by flood. This is more for urban areas, and we need to make a geoprocessing. And then we go to the field and collect the data of the impacted areas, and then we mark these areas, the risk areas for floods. So this is what I want to tell you, and I am open for any kind of question and information that you need. Thank you for your presentation and highlighting the importance of these areas, the importance of the work you do in this area to collect this data. And this is something that we can collect together to update the map of floods. So collect this information in the field as well as the remote assessoring that will give this realistic thing of the areas that can be flooded. So thank you.
Just wanted to say hi to everyone and thank you for inviting USGS to give a presentation today. So I'll go ahead and get the presentation queued up, and I'll just turn my video off as I'm presenting.
Right. Thank you very much for being with us. Thank you very much. We really appreciate your effort being here. And you're a host right now. You can present.
Okay. So hi, everyone. My name's Athena Clark. I'm with the United States Geological Survey. And once again, thanks for inviting USGS to give a presentation at this workshop. My presentation is on new approaches to event monitoring. And I just wanted to call your attention to the USGS stream gauges. There are over 10,000 stream gauges nationwide. And you can have access to the real-time data on many products, but the two main products are USGS Water Watch and then also the National Water Dashboard. The Water Watch is probably it's the flagship product for USGS. However, USGS is migrating to the National Water Dashboard. So don't get too used to WaterWatch because that will eventually go away, and you'll have to use the National Water Dashboard to access the data in the future. So today I'm going to give you an update on various tools and products to include the Flood Inundation Mapper, the USGS Flood Event Viewer, the high-vis dashboard, and the real-time flood impact map. So the Flood Inundation Mapper is where we're working with communities to protect lives and property. The mapping program has two main functions. First is to partner with the communities to develop and validate the flood inundation map libraries, and then also to provide this information online. So if you look at the mapper, you see all these triangles. Those are the locations where the flood inundation map libraries exist. And you can click on the triangle to expand that information further. When you click on the icon, you'll see several tabs going across. And the first tab is on site info and conditions, where you get the station number and the current conditions. Now there's a slider bar that you can see on the upper left. I don't know if you can see my pointer here. There's a slider bar that you could use to slide the gauge height up and down. And so, for example, I've got this gauge height set at 9 feet, and this gives you an idea about the flood extent when the gauge height is at 9 feet. And then also, I could slide the bar all the way up to 33 feet, and then you can see the flood extent at 33 feet as well. You can also use your pointer to hover over and get the water depth in that area as well. The next tab is the actual hydrograph, where you have the current conditions relative to the forecast conditions as established by the National Weather Service. And then there's a historical flooding tab. Within that tab, there's actually two tabs. The first one is the top 10 annual flood peaks. And then the second tab is the annual peak floods. And this particular gauge goes all the way back to 1895. We also tie this information to HAZUS. So based on the layer that you select, you can also get an idea about what the losses are, the total losses. And then links to the various metadata and API services. And some gauges have webcams, and so you have access to the webcams as well. This is another new product called the high-vis dashboard. And there are several gauges that have cameras nationwide. There's over 500 cameras, and we're adding them at a rate of 5 to 6 a day. Many of the sites pair still frame images with an interactive hydrograph. And I am the coastal storm team leader for USGS, and the coastal storm team is a large multidisciplinary group of folks comprised of USGS and select partner agencies that you see listed there. And we're activated as necessary in response to tropical and extratropical storms. So we have folks from NOAA, FEMA, Corps of Engineers, state agencies that call in, and it's our collaborative space, so we can hear from each agency what each agency is doing in response to that storm. Now, USGS operates and maintains the over 10,000 stream gauges nationwide. These are permanent gauges. I've got an image here on the upper left. But during hurricanes, we increase our data collection. We deploy pressure transducers ahead of the storm to document the timing and magnitude of the storm surge. We'll put out temporary gauges, also known as rapid deployment gauges, at ungaged locations or at places where permanent stream gauges have been damaged. And then depending on the nature of the storm, some storms will cause a lot of flooding. USGS will go out and collect high water marks to document the extent and magnitude of that flood. And most of this additional work that we do is covered by the Federal Emergency Management Agency. All the data that we collect during hurricanes is put into a product called the USGS Flood Event Viewer. And here you see the Flood Event Viewer for Hurricane Ian. The key about the Flood Event Viewer is the word event. So there's no other USGS product that is a compilation of all the data that's collected for a particular event. And so for Hurricane Ian last year, USGS deployed over 390 pressure transducers ahead of the storm. You can view the data and download the data from the Flood Event Viewer, and you also have access to all the real-time stream gauge data at this site as well. Now, the data that we collect during the storms, those pressure transducers that we install are not real-time. We do have to wait till the storm passes and go out and collect the data, download it, process it, and this is what that looks like. The graph that you see here shows the red line, which represents barometric pressure. That's very classic, drop in barometric pressure as the hurricane's making landfall. The gray line is what we consider raw data. Basically, consider that like the total water level that includes, you know, the components of wave. And then we apply a filter to remove the components of wave to estimate what we consider is storm tide, and that's the blue line. And then we also record the peaks of those. So at this particular site in Fort Myers, the total water level was considered 15.56 feet, NAVD 88, and the storm tide was considered at 13.23 feet, NAVD 88. Now we are experimenting with delivering the data in real time. There are some advantages to having gauges, you know, on site ahead of the storm. The nice thing is that you don't have to chase a storm. It decreases our time in the field. It increases safety, and it is data now. So folks do not have to wait for a week or 2 weeks to get the data. They're getting the data now. We have some examples of some of these test sites throughout the country in Florida, Alabama, Mississippi. I'll just go through them very quickly, give you an idea what they look like. And it's really nice to have real-time data. So say, for example, if you see this red line right here, which is the estimated landfall of Hurricane Ian, just to the north of it, we can see hurricane force winds pushing water away from the coastline. And then at this particular site, just to the south of it, you can observe the storm tide in real time. I'd like to shift over to another new product called the Real-Time Flood Impact Map. And the Real-Time Flood Impact Map shows the impacts of critical or safety infrastructure features near USGS stream gauges. And so this idea came from just comments from the public, you know, viewing the hydrograph. There's often a question. I understand this is water level, it's rising and falling, but how am I supposed to interpret that? How is that relative to what's going on in the real world? Here are a few questions that came in from the public. Are there any classes that can teach someone as ignorant as myself what all this information means? How do I apply this to my home and roads? And then the other one here is perhaps too local, but can you tell me at what gauge height does Highway 730 flood? So back in 21, USGS, NGWAS stands for Next Generation Water Observing System, funded the development of this real-time flood impact map. It lets the gauge tell the story of the flooding conditions going on in the vicinity of the gauge. And basically, we will go out and we survey the height. We survey the height, and then we also get the location of various features such as bridges, roads, and we associate that with the nearest USGS stream gauge. And when the gauge height exceeds that surveyed elevation height, then a special icon will appear on the map showing that location may be flooded. So when you go to the real-time flood impact map, you'll see all these white circles on the map. And those are the locations where we have currently conducted the survey. Also at the site, there's a date picker where you can go back in time and retroactively view the flood impacts. This is not a flood warning system, but it can be used to convey those immediate flood risks by showing those locations where flooding may be currently or soon occurring. And we have many different additional layers on the product to include access to the stream gauges, FEMA's flood hazard layer, we've got radar, we've got the watches and warnings, and we also have the NOAA tide gauges on there. And here recently, we have a Spanish version of the product. So if you do see an icon, that means that there's flooding going on at that location, and you can click on the icon and you'll get this pop-up. And in that pop-up, you'll see the hydrograph, but in addition to that, you also see the elevation of that impact, such in this case here, it would be a road. The nice thing about this is if the site is a flood forecast site, we will also show the forecast. And this is very important for local emergency responders because now they will not only know that, for example, in this case, the road is flooded, but actually how long that road will be flooded. That would help them determine how long to keep that road closed. There's also a subscription to a product called USGS Water Alert. And Water Alert is where the user can subscribe to the gauge. You don't have to look at a computer all day long and look for the data. Basically, you can subscribe and let the data come to you. So in this case here, if I want to be notified that this particular road is flooded and I know the elevation is 8.2 feet, then I can use Water Alert to subscribe to that. And once I get the notification via email or text message, then that's my cue that the road is flooded. Some additional information is USGS is working on developing an API for this product, which will allow us to incorporate it to other USGS products, such as the National Water Dashboard. Other agencies, such as the National Weather Service, can incorporate it into AHAPs, and Google Maps could also incorporate it. We currently have a JSON output file. And right now we are going through a discovery project within USGS to determine where we should add this additional flood impact layer. And there's consideration to add that to the National Water Dashboard. Some science centers are getting very, very creative. So if you look at the map now, we're have already surveyed over 350 flood impacts. We are partnering with Silver Jackets Corps of Engineers to get some surveys done. And we're also exploring ways where we could possibly use LiDAR to pick off the elevations. Here's a screenshot of just last week where this was a Silver Jackets project where the Corps of Engineers did the surveying. And this was an alignment of the atmospheric river that occurred in Washington State. And at the same time, we just finished up the project and had entered the flood impacts. And we can also see these flood impacts on this map now as a result of that. So this particular road, actually, I checked this morning, is still flooded. Just changing gears here a little bit. I just want to go back to these gauges. They have a very small footprint. We've been testing them in coastal, but they can be used everywhere. And one of the things that I do with my job as coastal storm team leader, I do look at our gauges quite often. And many times I hear, about flooding, flash flooding, and I don't see them on USGS National Water Dashboard. And the reason for that is very, very simple, is that you need to monitor the site in order to know what's going on there. So it's a very simple answer. Here's an example of Hurricane Henri with New York City, streets flooded, basements flooding. And if you look at USGS Water Watch or National Water Dashboard, you don't see that, and that's because we don't have monitoring at that site. So the reason why we call a stream gauge is because it's in a stream. But Yes, we could monitor storm drainage systems. We can monitor for street flooding. And if you think about the very small footprint of some of these sensors, they can be installed on telephone poles and light poles. We could survey in the elevation of streets and put that elevation into the real-time flood impact map. So this is the early concept of the product, and special thanks to our next generation water observing system that turned this little cartoon into a reality. And it's all about just letting the gauge tell the story. So what's there 24/7 during flooding? It's the gauge. So it's just so simple. It just might work. The nice thing about the product is that it is very inexpensive. All you need is a string gauge, and all you need is a surveyed XYZ, latitude, longitude, and elevation. And this gets to the heart of the USGS mission, which is to provide data to protect life and property. And the really, really nice thing about this product is that you don't have to be an engineer or a scientist to understand the hydrograph. You don't have to try to interpret the hydrograph. And that concludes my presentation. So thank you very much for inviting me, and let us know how we can help you.
Thank you, Athena. Thank you very much. We appreciate your presentation. We do have lots of questions, but don't have the time to ask you right now. So probably we'll stay in touch and talk more in the future. We do have, similar problems related to how to maintain this large set of stream flow gauges and what to do with those gauges when you have a flood, because lots of the times the gauges are, washed away with the flood and have to fix them again. So it's kind of operation of the gauge are some of the problems we face here. But hopefully can have more conversations and more contact in the future. Thank you so much.
Now I'd like to transfer the floor to George Bartolo of Semadem. Good afternoon, Alan. Good afternoon, everyone. So once again, good afternoon, everyone. I will make my presentation right now, and I hope I will try to fit this presentation on the time, but I will talk a little bit about what Semadem does, this National Center of Monitoring and Alert for Natural Disasters. And this presentation will be done not only by me, that is George, but also by the researcher Mariane Assis, and she'll talk a little bit about what was already mentioned here and other times in this workshop. Before I start, I would like to apologize myself, but before I would like to thank for the invite of this, to have this room here, this space of Semadem, that is an institution, it's a federal institution that contribute with this in floods, critical events. And firstly, I'd like to thank the event, and I hope it will be very rich and contribute to the dialogues and research of these institutions, Brazilian ones and foreign ones that are participating in this event. So the presentation here, in a brief way, I will mention the presentation of our center, then the monitoring and alerting Semadem, and then a little bit more specific about the hydrological monitoring and tools, and then a little bit about some questionings about the hydrological monitoring, how it could be more active in the vulnerability issues. And then I transfer the presentation to Mariane, that we talk about the better territorial and statistics base of risky areas together with IBGE. So Semadem, to present this, surely most of you already knows our history. It was created in 2011 after the disaster that have occurred in Rio de Janeiro, involving regions of Petrópolis, Teresópolis, Nova Friburgo, and that were impacted. So in that disaster, Semadem was created as a federal institution that belongs to the Ministry of Mine and Energy. And we have worked in two sides, dissociated, but created with the attributions to monitoring and issue the alerts, and also execute the researches related to the disasters. It means after some years, CEMADEN started to be seen as a unity of research of the country to give this scientific baseline to the disaster, not only monitoring and alert, but also the research. So CEMADEN worked in these two areas. One is more operational, one to monitoring. I will mention a little bit afterwards, but also the research that work together with another areas that are not linked to the operational one, but the research executed, because we issue all the reports from the side of the research. So I belong to the operational area, so I will focus a little bit about this part of the operational part of this operation room that we have, this monitoring room. CEMADEN here in Brazil also has this property to work 24/7. It means that is an activity that's not interrupted. CEMADEN today, it's responsible for monitoring 1,058 municipalities around the country. It was 1958 and around a year and something. But now we have these municipalities and we make all the forecasts. We have the projections to increase this number. And our monitoring team in CEMADEN to present these non-interrupted activities is compounded by professionals from these four areas: natural disaster to contextualize the municipality that could be impacted by these natural disasters, with analyze some conditions of these risk areas, the context of all the past events. It also has a professional of meteorology to give all the forecasts, weather forecasts that we have and need. So this is professional responsible for the forecast. We also have a professional about geoscience that is responsible to issue the alerts, as well as the professional from hydrology that I am part of it and responsible to send these alerts of floods and flash floods, considering all the forecasts that we have. So the alerts of CEMADEN, if I will be brief with that, CEMADEN, this operational, this monitoring room send alerts for the municipalities, alerts of floods, flash floods, and mass movements. The levels of these alerts, they could be, their general rule is that this alert initially is monitoring according to the conditions to be elevated, but firstly they are moderated, high, and very high according to the weather conditions. And then we started and send this to the level to finish this. But some alerts can be opened in a very fast way. Everything depends on the weather conditions, and sometimes we have critical conditions. Depends on the conditions of these municipalities. The sequence of these alerts, today we do it in a very fast way, but once it leaves CEMADEN room, it reaches Senad, and then it's sent to civil and state society to work on these events. This alert can be sent by WhatsApp groups, and these alerts basically works and is sent to Senad. It also reach all the civil defenses in the states. So here, in a very brief way, here we have our main tools that we use inside CEMADEN to make this monitoring. Salvar, it's our platform of data visualization. This is our visualization program where we have different data that are loaded here according to the preference of the analyst that is working that moment, to possibly make a decision. These municipalities are the municipalities that we can see the dots on the map. As it was already shown here on the map, we have the main concentration of these critical areas are here in Amazon Basin. Also comes to the shore region, and also other municipalities that we have that are more continentals that are also monitored, respecting each characteristic of their geography. I'm also showing here the covering of the rain gauge that we have in our systems. We have all the rain gauge of Semadem around the 3,000, Ana and other smaller institutions, state or municipal ones. Here we have our radars, and we also use here in some cases when we have the pluviometric levels. The same way we have the information of Semadem, we also use even more, we use the systems of ANA and CPRM. So we have a big amount of information that we use to think to help us in our decision-making process of alerts, if we have to send the alerts or not in the areas we are monitoring. And here in this slide, I put this in the general way, the risk areas, the vulnerability, and this is the source of information that we have. We have in Semadem today, we have those maps of CPRM that was created in 2011, 12 until 14. And this updating is not done with the frequency that we had regarding all the sensors we have in those areas. What I would like to emphasize here in these risky areas is that we have estimated population that are in that area, the river that is crossing the city, which neighborhood is closer to a risky area. So it is important to emphasize that Semadem does not work risking area. What Semadem does is send the alert to the municipality, because what we expect is that Semadem helps the municipality monitoring, but the ones that have to take the decision facing a disaster, possibility of disaster, is the civil defense, the local civil defense. So this is what we do, considering the maps, according to the information that we have. The municipality is the one that we have more knowledge of possible disasters or necessity to make any kind of intervention. So this is what we use here. This is another mapping tool that we use that already brings some information about possible vulnerabilities of each municipality. Vulnerabilities that I also like to say that when we analyze my speech here, it was a very wide concept. We mentioned a lot vulnerability, but it's also confused itself with the sensitiveness. So I can say that we don't make this vulnerability analysis with the frequency that you could imagine, because we look more the numbers that are just in that time, and the vulnerability sometimes already gives some excerpt of the information we already have. So if I know that it will rain 50 millimeters in one day, I already know that that municipality has a vulnerability, but it's also likely to suffer the impacts. So the vulnerability is already included in the decision-making process, because people already know this information before that process. So just the current perspective we have in our hydrological system in Semadén. We have the modeling that is in the implementation, this modeling for the researcher Roxanne. She has presented already this project, some basins, I think Rio Doce and Tocantins River, that is already the role that was executed by the Federal University of Rio Grande do Sul. It's a system that kept hydrological forecast and the inundations, and then they have a permanent curve over a linear, and after that they give the possibility of a flood based on that. So it's a model based on statistics. So this modeling is already inserted on Semadén, but probably the trend is that we increase the number of bases according to this. I can detail that later. And the automatized risk forecast, we already use this in Semadén, and there we do it every day. And we have as initial result in automatization of this risk forecast. And the question is how we can improve the inserting of this vulnerability in a global monitoring. This is something good and robust, but we have a lack of view how we can make this information become more present in our decision-making process to issue an alert. So here I give you some suggestions for future contributions, and I think Mariane will explain it also. So this is what I tried to make this link, this correlation, to let you know how it is, to mention the vulnerabilities we have in Semadén. And now I give the floor to her. Mariana, if you're already there, you can, the floor is yours. So I am Mariane Assis. I am an expert in vulnerability and research of Semadén, and we have worked with IBGE in a consistent project since 2013, aiming to identify the population that is living in a risky area in Brazil and quantifying not only it was something that had many tries in CPRM, but also characterize this population so we could have some vulnerability characteristics. Of course, in this context, the vulnerability is a vulnerability associated with a demographic profile, social vulnerability. So I will put here for you few parts of this project. Here, part of this project. So we have consolidated them in few scientific papers, and I already put this for you so we can download it if you want to read all the methodology that was used. But here the idea is that we could add the information of this mapping, integrating the risk integrating produced by CPRM or another source, if there is another source available, and associate them with the another sectors that are the polygons that are associated to demographic information produced by the census, or more refined data from census. It's face of block, where each face of block you already have an information that is associated of population, and information of the population of inhabitants, and the characteristics of age, range of age, literate or not, if the characteristics of the house, but it's also with this bias to aiming to look at the population that is living in a risk area to reach this number. So here another paper that we have produced with the exploratory analysis, socio-demographic ones with 825 municipalities, resulted from the estimation of census of 2010. We are expecting the census of 2022, but this estimation is 8 million 266 people that are exposed to risky landslide and 27,000 in risky areas in Brazil. In this graph in Brazil, we can see here in this table the risky population according to the regions of the country, but this is a very disaggregated and even more detailed in risky areas. We have even more detailed, and then we can have this view of this population in a risky area. Just remind you that this part, it's not a risky area. This is a territorial basis to be associated to this data for the risky area together with that sensor. This is important to make it clear to do not use butter. It's a meaning of a risky area because generally this butter area, as I mentioned here, it can be bigger than risky area to incorporate more than one area and so on. So we must care about this once we use this data. This is closer data where it was closer to make the association of the social demographic census. And here effectively to implement this Brazilian alert system, we had a paper of identification for risky population to help the alerts. The biggest aim of this beyond to know where is the people that is in the risky area and issue policies, but we also in this risky management, we should find the north of action at the time we issue the alert to identify and say, well, I know, as George say, I know there is a rain scenario here. I know this scenario can impact in the municipality, but will that achieve all the municipality considering the vulnerability of the population? So we have some areas where we have a more affected population will be the population that is living in high vulnerability area according to the delimitation of what is this high vulnerability. So this vulnerability for us, as it was said here, we are looking at the social profile. So the vulnerability is based on the capability of answer. So we use the index of population based on the answer capability and also the capability to promptly respond to this event that the population is exposed. They already lives in the risky area, and the capability to answer and the situation, because there are situations that we have more vulnerability with elder people, children, people that live in houses that have problems. These are points that will show us the vulnerabilities, and it was done in the data collection we did in this demographic study to reach these conditions. So then we can identify here the amount are from 443 municipalities we identified according to the phases of vulnerability, how this population was split. Population with a high population around 2,006,000 people, high vulnerability 10 million to 100 million, and medium and low vulnerability. And the interesting part of this paper is that we made the association, we identified the vulnerability where these people are distributed here, all the municipalities. We did this study crossing the information based on past event, and mostly where we identified effectively where we have this occurrence of disasters in high disaster causing impact and deaths. These are areas that were identified according to meteorology, that this index, it was identified as effectively we had deaths, and the vulnerability was identified as a very high or high. So here we can see a good adherence, a good index that could reflect effectively all those areas that must be prioritized when we are issuing an alert, because instead of civil defense does not know where they should go to, we can north this action considering all the characteristics and the distribution of the population if the rain is a threat. So this is what we try to make this insertion considering the meteorological conditions, being the rain forecast, distribution of this rain gauge, distributing the radars and identify this situation that is very dynamic with more static information according to the profile of the population that lives in that area, because these are information that are updated according to the occurrence in every 10 years. Of course, we had a biggest problem. So we have this expectation from next step that is waiting for this data from 2022, have this updating of municipalities, updated the risking areas if necessary, and from this study of ANA, we can even, if necessary, insert this part of ANA and show these vulnerable areas for these hydrological risky areas from the most susceptible areas. So we can think in incorporating information of population in this area, because having that available in the distribution system, the distribution of each area, we can of course try, not in the river of course, because not in north region, but where people are effectively living, but maybe an insertion area, try to incorporate and identify the population that can be potentially impacted by this hydrological event. So we can think about it. I think this is a contribution for SEMADEN and IBGE and ANA that can make this contribution, this integrated contribution, and it can also move forward with the vulnerability risk area. And that's it. Perfect, Mariana. Thank you for your presentation. Thank you, George. Thank you for SEMADEN for being here. These are very important studies that you have presented here. I just would like to make a quick question here. But this study that was done here is a national scale for all municipalities, or only for those that you have notified previously? No, this is for the municipalities where we have the mapping, we have cut data, we have 825 municipalities, but we are already updating this, but this methodology was done to be used in any municipality that we have all this kind of information. If we have the information of the census that is done in all municipalities on the other side, we just need this information of the risk mapping of the other areas that we have to make this association between one thing and another, because the modus operandi is how this association is done, and base data we have already set this previously perfectly. So this risk information comes from CPRM, correct? Yes, CPRM mapping and what they could put together in their studies. So it was perfect. Surely we will be in contact with you to talk about this a little bit more and unite our efforts to update all this information. With the CPRM, we have been talking to them also. So each institution, I think, is making its part in the process, so we could put all the efforts together and have something more robust and complete according to what the institution has as an expertise. Yes, and we are available to include this information of population. I think it could be very interesting to all of us. Perfect. And another thing is, here in the chat, people asked if you could type the link or the papers you have shown here. I typed my email, so this isn't an open access yet, but I can send for those that will write to me. These are 3 files actually. So Laura that asked here, Laura, if you could get in contact with Mariana, that would be great. So she can send all the papers for you. So now I'd like to finish this long and very rich afternoon. I would like to thank all the speakers that we have here for the presentations. You all have done with so much rich details and information that give us so much references and give us a baseline to move forward in this process to update the vulnerability in Brazil. I also would like to thank you all that are together with us, the audience that were with us here, be in contact with us to get more information. Our wish is that we could interact. This is our first event in this process, as Vinicius mentioned, so this update is in the National Hydric Resources to finish this until 2026. We want to finish this before. We want to make it by region. We already have information from South region, and then started with other regions, Northeast, Southeast, and prioritizing the areas that are more vulnerable and updated this information. And then we can do it, of course, together with all the institutions and with the feedback and interaction with the technical community that is involved with this topic. So we will inform you about our next steps as soon as we move forward. So thank you once again. I also thank to the interpreters and the team that were here supporting us. I'm sorry for the time that it lasts. We calculated something, but we had too much information, the presentations, but I think at the end we had a good event. So with that, I thank you, all of you, for being here, and I close this section. Thank you very much. Good evening to all of you.